Hello and welcome to Sleepy Science. I'm so glad you're here. What if tonight we set aside the word particle and let the world reveal itself as fields? Quiet fabrics that ripple, quantize, and conjure excitations with the lightest touch. We'll meet creation and annihilation as simple moves in a cosmic score. Discover spin not as twirls, but as how fields carry symmetry, and see gauge freedom as redundancy that secretly wires forces together. We'll taste Yang-Mill's confinement, stroll through path integrals like soft rain on possibility, and watch the renormalization group flow like a river down theory space. We'll stack effective theories in honest layers, break symmetries to hear Goldstone whispers, and feel mass as a medium story in the Higgs. Topological terms will sketch edges that conduct while interiors rest. Anomalies will show how perfect rules bend just enough to match reality. We'll wander vacua with many minima, bounce on instantons, peek at holography where gravity and fields trade places, and trace entanglement wedges as geometry emerging from correlation. Lattices will approximate the continuum, anyone's will braid identity. We'll visit the early universe, scalars, inflaton, Axion hints, then meet spinors, photonic playgrounds, and open fields that hum with baths and noise, ending where particle intuition misleads most. Where are you listening from, and what time is it? If this gentle wander helps you rest, please like and subscribe so more sleepy minds can drift here. Now take a slow breath, feel the bed hold you, and let's begin. What a field is really. Before you ever meet a particle, you meet the quiet pattern that could make one appear. A field is that pattern, a rule that gives every point in space and every moment in time a specific value that can change, spread, and interact. So when you hold out your hand to the air, you're not touching emptiness but standing inside overlapping fields that gently describe temperature, pressure, light, gravity, and more, all at once. The simplest way to feel it is to imagine a perfect weather map that never stops updating. Each location gets a number for warmth and perhaps a little arrow for wind, and now replace weather with reality, because in physics, a field is the map and the territory together, the continuously defined amount of something that exists everywhere, even if that something is just a potential for action until you disturb it. And you will learn more clearly by walking step by step from ordinary experiences to the idea that modern physics is less about tiny marbles flying around and more about ripples in underlying mediums that fill the stage. You've met scalar fields without thinking of them as exotic. Temperature is a single number at each place, and a scalar field is exactly that, one value per point, while a vector field attaches a little arrow to each point, like wind direction and speed across a valley or ocean, and more intricate situations in materials or in space-time use tensor fields, which you can think of as structured packets of directional information that tell you how a thing responds when you push or twist it from different angles. With these examples, you already have the toolkit to picture electric and magnetic fields as structured assignments spread throughout space, to picture the stress inside a crystal as a field telling each tiny patch how it strains, and to picture gravity, at least in a gentle sense, as a field that tells things how to move, or in Einstein's deeper picture, a geometrical field that bends the paths available to everything. If you step closer, a field is not a fog or a jelly but a function with a physical job. It stores energy, carries momentum, and responds to sources. A charge creates and reshapes the electromagnetic field. A mass reshapes the gravitational field. A moving magnet rearranges space's bookkeeping so that what you call force on a conductor is the field transferring momentum according to precise local rules. And that word local matters because a field only updates using information from its immediate neighborhood. No instant distant whispers, and that's how causality survives inside a universe that respects a finite speed for signals to travel. When you flick a rope, the disturbance travels along it. When a lightning bolt forms, the electric field reorganizes and propagates, and when the sun shines, it is an electromagnetic field changing in a self-sustaining way that needs no material to ride on. Unlike sound, which is a pressure field in air or water, you can test the presence of a field by coupling to it with a detector, because detectors are just systems designed to taste specific field values or their changes. And this tasting is how telescopes, antennas, and even your eyes work, translating patterned variations in a field into patterns of nerve signals you can recognize as images or sounds. A helpful mental move is to think in terms of waves without getting trapped by the ocean analogy. Any shape a field takes can be decomposed into simpler notes called modes, like building a melody out of pure tones, and each mode has a wavelength and frequency that explain how the pattern moves and resonates. This superposition principle underlies why a guitar string can sing many notes together, why a light pulse can be a blend of colors, and why a radio station can ride on a carrier wave with subtle modulations. And although later we will talk about quantization, the laddered way energy comes in packets. Right now you only need the classical fact that fields can support waves whose shapes add and interfere, creating rich structures from simple ingredients. Energy in a field isn't mystical. Where the pattern is steep or intense, the field stores more energy density, and where it flows, you can define a momentum density, which is why the sunlight that warms your face can also push gently on a sail in the vacuum of space. Even without equations, you can hold on to the idea that energy and momentum are distributed and moved around by fields, and that boundaries in materials tell those fields how they're allowed to behave, the way a coastline shapes ocean waves, or a metal cavity selects which electromagnetic notes can stand inside it. Some fields are linear, their disturbances pass through each other like polite ghosts, while others are non-linear and can make waves talk to waves, exchanging energy, merging or splitting patterns so that a strong enough field can influence itself. And nature uses both kinds to create everything from clean, undistorted radio to violent solar storms that tangle magnetic lines in the sun's atmosphere. And because fields obey local differential rules, you can build reliable simulations on a grid, stepping time forward and watching the pattern evolve, which is how engineers design antennas and how scientists model weather, plasma, and even portions of the expanding universe. The word vacuum can be distracting, so ground it. For a field, vacuum simply means its lowest energy, undisturbed configuration, the calm surface before any wave starts. And while deeper quantum stories add texture to that calm, the basic classical picture is already powerful. If you leave a field alone, it settles. If you poke it, it responds. If you keep shaking it at the right rhythm, it resonates and can pump energy into specific modes, exactly like pushing a child on a swing with well-timed nudges. Interactions live in the way fields talk to sources and to each other. Charges source electric fields. Changing electric fields create magnetic fields and vice versa, stitching light into a self-carrying phenomenon. Masses and energy source a gravitational field that curves paths through space-time so that planets orbit and light bends near stars. In materials, fields couple to the ordered structure of matter, which is why a crystal can guide waves that vacuum wouldn't, and a superconductor can expel magnetic fields and make astonishing levitation tricks possible. None of this requires you to imagine invisible gears, just keep the rule in mind. A field is a space-filling assignment that updates locally, carries energy, and mediates influence. Your intuitions may try to pull you back to particles, because that's how our senses sample the world. Little clicks in a detector, little flashes on a screen, but the calmer and often more accurate foundation is that those clicks are consequences of how fields evolve and interact with measuring devices. And seeing it this way helps you avoid confusions later. A localized event is the field delivering energy in a small place over a short time, not a marble landing after a long flight. A beam of light is a traveling pattern of electric and magnetic values, not a thread of beads. And even in matter, properties like stiffness, heat flow, and magnetism are field behaviors distributed across space, not just traits of isolated bits. If you want one practical takeaway, let it be this. To understand how anything changes in physics, how signals travel, how forces appear, how energy moves, start by asking what field is present, how it's configured, what boundary conditions and sources it has, and what local rule it follows to update in time. That single habit ties together the way storms swirl on Earth, the way sound fills a hall, the way Wi-Fi reaches your phone, and the way starlight crosses a vacuum to your eyes. And as you sit with the idea, let it slow your thoughts in a comfortable way. A field is a gentle promise written everywhere, a promise that if you nudge the world here, a response will blossom nearby and then wander outward, carrying information and energy along lawful paths. The mystery isn't that fields exist, but that such simple local rules can weave patterns vast enough to light a sky, stable enough to build a life, and precise enough for you to listen, breathe, and feel the quiet order of an unseen map that is also the world itself. Quantizing fields, from waves to quanta. You've listened to waves your whole life, music in the air, ripples on water, the hush of wind. So the surprising step isn't that nature loves waves, it's that at a deep level the waves learn to count. And that counting is what we call quantization. Instead of letting a field's vibration slide through any energy at once, the universe quietly installs a staircase so each mode of the field can carry energy only in whole steps. And when you feel ready to see past the old picture of tiny marbles flying around, you realize that a particle is just one counted step in one vibrational mode of a field. Begin gently with a single mode. Imagine a pure tone you could whistle forever, not because there's a pipe or a string, but because the electromagnetic field, say, has a way it prefers to hum in that shape. And now add a rule. That tone cannot be energized by an arbitrary amount. It must climb rungs of a ladder, one rung per quantum, and the lowest rung isn't zero, but a faint residual hum that never quite goes silent, a clue that even the calmest field keeps a heartbeat you can't switch off. Stack rungs and you have 2 quanta, 3, 4, each step a clean packet of energy, and suddenly the word photon reads like a label on a rung rather than a bead in space. To reach this picture from the wave world you already know, you do something conceptually simple but profound. You take the recipe for a field's vibrations, the way you decompose any complicated pattern into a blend of pure notes, and you treat each note as if it were a tiny, independent musical instrument with its own discrete volume control. Turn it up by one click and a quantum appears. Turn it down and the quantum is gone. And because the clicks are identical, you cannot tag or follow a specific quantum like a painted grain of sand. You can only say how many clicks each instrument is set to right now. This is why detectors don't show a smooth smear of energy, but deliver crisp, countable yes events. Why a dim light still triggers single sparks on a sensitive camera. And why heating a cavity between mirrors changes not only how bright it looks, but how often those clicks arrive. Don't worry about heavy symbols. What matters is the pattern. Fields spread out, but their energies gather in packets. The packets are not marbles inside the field. They are the field when it carries the tiniest non-zero amount of motion in a particular shape. And when you change shapes, shorter wavelength here, longer there, you change which staircases you're climbing and how tall each step is. Because the size of one quantum depends on the note's frequency. So blue light's rungs are higher than red light's, which is exactly why blue light can kick electrons out of a metal that red light leaves untouched. Not because blue is angry and red is lazy, but because the blue staircase has bigger steps that can vault the barrier in one clean hop. Once you accept that each mode has this ladder, a new kind of bookkeeping becomes natural. You describe the state of the field by saying how many quanta sit on each ladder, like an orchestra score that lists how many flutes, how many violins, how many horns are playing at once. Add one to a mode and you've created a quantum in that shape. Remove one and you've annihilated it. Do this across many modes, and you can build a pulse that travels, a beam that focuses, or a pattern that spreads and interferes with itself just as classical waves do. Except now the energy arrives in indivisible hits that detectors can count without ambiguity. In a quiet lab, this shows up as shot noise, the graininess that remains even when you've silenced everything you can. A signature that the field's waves are made of steps rather than slopes. Notice how this recenters the idea of measurement. When your photodiode clicks, it is not catching a tiny flying ball. It is the field delivering one step of energy into the device in a brief interval. And the probability for that delivery depends on how you've prepared the field, how many rungs are already occupied, how the modes overlap with your detector, and how boundaries and materials shape the available notes. Place the field in a mirrored box, and only certain notes fit, like standing waves on a string, so the allowed quanta arrange themselves into a spectrum you can probe. Open the box, and the notes blur into a continuum, changing how likely a given click becomes. Two roads can lead you to this same destination. One begins by treating the field like a classical wave, and then imposing the counting rule so that energies climb a ladder. The other sums over all the ways the field could wiggle and shows that the most consistent outcomes behave as if the energies come in packets. But whichever road you walk, you land in a landscape where interference and diffraction remain perfectly wave-like, while energy exchange remains perfectly step-like. And living with both at once makes sense once you remember that wave describes the field's shape and evolution, while quantum describes how energy is carried and recorded when the field interacts. This stepwise structure explains real, testable things without heavy math. Why dimming a laser doesn't make its clicks smaller but makes them rarer. Why light of one color can trigger chemical reactions that another color of equal brightness cannot. Why cooled atoms fall into regular patterns only when the field is tuned to the right staircase, so each absorbed and emitted quantum nudges their motion by just the right amount. It explains why, in materials, vibrations of the atomic lattice, another kind of field, arrive at your sensor as counted packets of heat flow, and why detectors designed to listen for these tiny thermal quanta must be built like ears that can hear a single footstep in snow. Along the way, your intuition stretches in a helpful way. You stop asking, where is the particle right now? And start asking, how is the field prepared? Which ladders are occupied? And how is my measurement poised to exchange one counted step with it? That habit rescues you from paradoxes later, because it reminds you that clicks are not the primitive facts of nature, but the end of a longer story in which a prepared field and a prepared device meet under rules that allow only whole steps of transfer. If you change the preparation, squeeze noise in one property to calm fluctuations in another, shape pulses so that energy arrives in tighter bursts, place your system inside guides that select narrow bands of notes, you change the statistics of those clicks in precise, predictable ways that engineers and experimenters use every day. Let the conclusion be soft but clear. Quantizing a field doesn't crush the poetry of waves. It teaches you how the music pays its bills, one token at a time. And once you hear that rhythm, the world looks cleaner. Light becomes counted whispers of a continuous harmony. Matter's vibrations become parcels of warmth hopping from place to place. And your detectors, from your eyes to radio dishes to qubit readouts, become translators that tally those tokens. You breathe a little easier because mystery has turned into method. And you're ready for the next chapter, where we'll open the control panel behind those add one, remove one operations, and see how nature manages the counting with a calm, almost mechanical grace. Creation, annihilation operators demystified. Imagine being shown a control panel for a field where two simple buttons, add one, remove one, can build beams of light, cool atoms, strengthen vibrations in a crystal, or quiet the noise in a tiny circuit, and then being told those buttons aren't physical knobs but precise instructions baked into the way the field keeps score. That's the heart of creation and annihilation operators. They are the bookkeepers of quanta, the rules that say, increase the count in this specific vibrational note by 1, or decrease it by 1. And although the words sound grand, the idea is practical and testable because every detector click, laser pulse, and single photon experiment is a story of those counts going up and down under strict conditions. Start with one mode of a field, a pure note, like a clean tone in music. Creating a quantum in that note means raising the mode's energy by exactly one packet, and also handing it the right momentum and phase so it fits the note's shape. Annihilating means handing that packet to something else, an atom, a mirror, an antenna, so the field's count drops by 1, while the receiver's energy and motion change in a matching way. You never conjure quanta from nowhere or make them vanish into nothing, because conservation laws keep an audit trail for energy and momentum, and the add-remove rules are built to respect that audit at every step. If you could watch a dim lamp feed a sensitive camera, you'd see the panel at work. Each recorded spot is the field obeying a remove one here and now instruction, because the camera has the right internal structure to accept the packet. And if you swap the lamp for a well-prepared single photon source, those removes become cleanly spaced events rather than random crowds. revealing how the counting can be controlled. Flip the situation and pump a gain medium inside a laser, and stimulated emission is just the add one button becoming easier to press whenever a matching quantum is already present. One packet invites another into the same note, so the field's population in that mode grows rapidly and emerges as a tight, coherent beam that holds its shape over long distances. The buttons also explain why detectors and sources must be tuned rather than generic. An atom with two suitable levels isn't a loose bag of energy. It has a built-in doorway that only opens for specific colors and patterns. When a passing field matches the doorway, the remove one rule can execute cleanly, and the atom can jump while the field loses a quantum, or the atom can drop and press the add one rule into the field with the same color and phase. Off resonance, the rules simply don't line up, and nothing happens beyond a faint nudge, which is why selection rules in spectroscopy feel like traffic laws. They are the human-readable summary of when the add-remove instructions can legally run. Crucially, the buttons are not tied to a single place or device. They live inside the field's description itself, and the address label on each button tells you which mode it affects, what spatial pattern, what rhythm, what polarization. So to create in a focused spot, you don't press a generic add button. You prepare sources and boundaries so the mode you care about exists and can accept count increases. In a cavity with mirrors, only certain notes are allowed, and the add-remove rules refer to those notes, which is why the energy inside such a cavity comes in distinct amounts, and why the spacing between allowed colors is a property of the geometry. Open the mirrors, and the notes spread into a continuum, changing not the existence of the buttons, but the dictionary that maps them to actual patterns in space. At small scales and short times, the details of the buttons reveal deeper traits of nature. Fields whose quanta like to pile up in the same note, light, sound in a crystal, vibrations in a superconductor, follow add-remove rules that make crowding easier, while fields whose quanta are one per seat, like electrons, obey buttons that refuse to add another occupant to an already filled slot. A gentle way of saying that these add-remove rules encode the difference between pile-friendly and seat-strict quanta, and thereby underpin the stability of matter. In clean experiments, you can see these rules in statistics. Photons produced in many thermal processes prefer to clump in arrival times, whereas carefully engineered single photon sources yield arrivals spaced closer to 1 by 1, and electrons in beams won't share exactly the same detailed state, a fact that shapes everything from the periodic table to the way metals carry current. The operators also carry the timing for how modes evolve. Even if you don't write equations, you can keep this picture. Each add and remove instruction comes with a built-in rhythm, so that, as the field hums, the ability to press the button swings in time with the mode's oscillation. Press in step, and you escalate the population efficiently. Press out of step, and you mostly cancel your own effort, which is why driving a system at resonance is so effective, and why detuned pushes waste power. Engineers exploit this constantly, from pumping lasers to cooling atoms with light, to amplifying tiny electrical oscillations near a target frequency. If you peer into measurement, the buttons make the logic straightforward rather than mystical. A measurement device isn't peeking at hidden marbles. It's an interface whose internal modes are designed to run a controlled remove one or add one when the field state overlaps with its own. If the overlap is small, the chance is small. If the overlap is large, the chance rises. And by shaping the device, its geometry, materials, and timing, you shape the map between the field's prepared state and the distribution of outcomes you see as clicks, pulses, or voltages. This is why changing the aperture of a detector, the dwell time of a readout, or the reflectivity of mirrors doesn't just collect more light, it rewrites the likelihood of specific add-remove pathways firing. Even in the gentle limit where only a few quanta exist, the operator picture explains interference with clarity. Two paths for adding to the same mode can reinforce or cancel depending on their relative timing. So you can have setups where increasing the chance along one route actually lowers the total detection rate because the add histories step on each other's toes. In reverse, two decay paths from an excited atom can be arranged to cancel, delaying emission A laboratory trick that shows the count-changing rules are sensitive not just to how much energy is available, but to the phases of the processes that deliver it. All of this makes the operators feel less like abstract algebra and more like a user manual. They tell you how to build sources that add one at a time, how to shape cavities that prefer certain notes, how to design sensors that faithfully remove one without losing information, how to suppress noise by steering fluctuations away from what you care to read out, and how to choreograph many modes so energy flows where you want it. They also keep you honest by encoding conservation laws so that your designs never rely on forbidden moves. Let the close be calm. Demystifying creation and annihilation operators is not about memorizing symbols. It's about recognizing that nature gives us a crisp grammar for changing the population of field notes. One step at a time, with timing, shape, and symmetry deciding what's allowed. Once you hear that grammar, detectors become conversations rather than surprises. Light becomes a score you can compose, and the quantum world feels less like a magic show and more like a studio where small, exact moves add up to clear, reproducible songs. Spin from representations, not tiny twirls. You've been told spin, as if tiny objects were whirling like tops. But the truth that unlocks everything is quieter and stranger. Spin is not a miniature twirl in space. It is a promise about how a quantum state responds when the world is rotated. A built-in instruction that says, if you turn the laboratory, I will change in a precise way. And the allowed ways form a small catalogue called representations of the rotation symmetries. Pick one entry from that catalogue, and you haven't chosen a speed of turning. You've chosen a character in nature's script for how the state transforms under rotations, and that character's name is the spin. Begin with a simple thought experiment. Imagine the entire apparatus, the magnets, the detectors, your reference arrows, being turned slowly about some axis while the system under study sits there. Classically, nothing about the object itself would care how your coordinate arrows were drawn. But in quantum mechanics, states carry transformation rules tied to the symmetries of space. And those rules are not optional decorations. They predict the discrete results you actually measure, like the two clean beams in a Stern-Gerlach experiment, when silver atoms pass through a magnetic gradient and split into up and down paths, not because the atoms contain tiny bar magnets pinned in one direction, but because their internal state transforms like the simplest non-trivial representation of rotations, which has just two perfectly stable outcomes along any chosen axis. This is the first clue that spin is a transformation label, not a little wheel. Try to imagine an electron as a ball spinning fast enough to create its magnetic effect, and you run into impossibilities. Surface speeds would have to exceed light to match the measured magnetism, and the inferred size from scattering is far too small for a classical spinning sphere. Yet the electron's spin shows up reliably in every measurement, leaves fingerprints in spectra, locks into patterns in solids, and controls how atoms build the periodic table. The only coherent way to hold all these facts is to say that spin summarizes how the state behaves under the symmetry of rotations, and that behavior is inherently quantum. Rotations in three-dimensional space form a specific symmetry family, and quantum states are allowed to realize that family in distinct ways. Some states return to themselves after a full turn. Others need two full turns to come back to where they started. And that latter possibility, the need for a 720-degree rotation to regain the original state, has no classical twin in whirling marbles. But it is seen in interference experiments that can tell the difference between a once-turned and a twice-turned state by letting them recombine and watching the pattern shift. This two turns to reset behavior is the hallmark of half-spin, and it explains why certain particles make two output beams rather than 3 or 5 in magnetic splitting. The representation they live in has precisely two stable projection values along any axis. If you prefer a picture, think of a compass needle that can only point north or south relative to whatever axis you define. But every time you rotate the apparatus, the meaning of north and south is redefined by a rule tied to the state itself. The outcome in a fresh measurement is not random mood, but a direct response to that transformation law. And switching axes changes the probabilities in a way you can calculate once you know the representation label, which is what physicists call the spin quantum number. This label does much more than set the count of beams. It dictates how the state combines with other states when you bring systems together. Two-valued spins can merge into a three-valued family or shrink into a single quiet channel, depending on how their transformation rules intertwine, and that explains features of magnetism in materials, the splitting patterns in atomic energy levels, and the selection rules that decide which spectral lines appear and which are dark. In solids, arrays of such two-valued rotators can lock into long-range order, giving ferromagnets their personality, and in nuclei, families of these transformation behaviors stack into intricate patterns that show up as the spin and parity of nuclear levels read by gamma rays. The idea extends with variety. Particles without mass, like photons, cannot be brought fully to rest. So, their spin shows up as helicity. Handedness of their fields swirl along the direction of motion, and only certain options survive the constraints of moving at light speed. That's why you meet two polarizations of light in the lab, and why very different systems, from radio waves to laser beams, to the microwave echoes left from the early universe, carry polarization patterns that map the distribution of these transformation properties across the sky or across your device. Once you grasp that spin is a representation of symmetry, long-standing puzzles soften. Why does turning the apparatus change the statistics of up and down in a perfectly predictable way? Why do interference patterns shift when you rotate a sample of spin-carrying particles before recombining their paths? Why do some lines in a magnetic field split into two while others split into more? Why does a medical scanner tuned to a particular frequency coax tiny compass needles in your body's water to tip and realign, lighting up tissues in shades that reveal structure without a single cut? Each answer is because the states transform under rotations with a specific rule, and we are driving or reading that rule. Even the delicate detail that some systems require 2 full turns to return to their original state is not an abstract curiosity. It is measured in molecular beams, verified in neutron interference where flipping the spin in one arm shifts the fringe, and exploited in quantum technologies that store and manipulate information in the controlled orientation of a two-valued rotator, the way a pianist might shape a chord with tiny changes in pressure. Importantly, the representation viewpoint helps you avoid seductive but wrong pictures. There is no need to imagine a spinning surface, no need to assign a literal size or edge to the spinning part, because all the reliable predictions come from the transformation rule itself. When a magnetic field nudges a spin, it is aligning a transformation preference with an external direction, which causes the state's internal bookkeeping to precess like a gyroscope's axis in gravity, and that precession has a measurable rhythm that underlies nuclear magnetic resonance, electron spin resonance, and modern techniques for sensing fields so faint they could be fingerprints of brain activity or whispers from dark matter searches. If you want a clean, practical summary, you can carry into any experiment. Choose an axis, and a spin-labeled state offers you a menu of discrete outcomes along that axis. Rotate your apparatus, and the menu remains the same, but the probabilities reshuffle according to a fixed rotation rule. Couple gently with the right frequency, and the state will tip and precess, trading weight between outcomes in a rhythm that encodes both the strength of the field and the representation label. Bring 2 such states together, and the joint menu is not a simple list of pairs, but a recombination governed by how the symmetries compose, which is why pairs can cancel or reinforce, and why some combinations are forbidden. Let the closing be soft but firm. Once you see spin as behavior under rotation, the quantum world looks less mystical and more organized. The 2 beams in a magnet, the double turn peculiarity, the clear rules for adding spins, the polarizations of light, the crisp control in magnetic resonance, all line up as consequences of the same quiet idea that matter and radiation carry identities defined by symmetry, and those identities are not pictures of spinning stuff, but living instructions for how reality responds when you gently turn it in your hands. Gauge symmetry, redundancy that reveals forces. You've used gauge freedom your whole life without naming it. Every time you shift all voltages by the same amount, and nothing physical changes. Every time 2 maps draw the same city with different 0 points or color schemes, yet the roads and travel times stay identical. You are touching a quiet idea, redundancy in description. And the shock in modern physics is that this redundancy isn't a flaw to be cleaned up, but a principle so strict that when you demand it to hold locally, forces appear as the price of keeping equivalent descriptions, equivalent at every place and every moment. That is gauge symmetry in one breath, and once you see it, many puzzling facts line up. Start gently. In electricity, we care about potential differences, not the absolute number you write in a corner of a schematic, because only differences push charges. This simple shift doesn't matter rule is a global freedom. Change. Everything by the same offset and predictions don't budge. But nature goes further and allows you to change the reference differently from point to point, like letting every neighborhood choose its own zero for voltage or its own internal clock hand for the oscillation of a wave, so long as you adjust an accompanying field that keeps neighboring choices compatible. That accompanying field is not decoration. It's the electromagnetic potential, and its job is to connect local choices so that a charge moving from one patch to another can compare notes consistently. And when the connection twists in space or time, you feel that twist as electric and magnetic effects. This is the first deep lesson. The gauge field is the bookkeeper that guarantees your freedom to rephrase things locally without changing outcomes. And the patterns in that bookkeeper are what we call forces. In practice, this shows up when the rule, differences matter, absolutes do not, is made local. If you let the complex phase of a matter wave be redefined independently in each region, think of it as allowing every town to set its own midnight. Then to keep interference predictions intact, you must introduce a field that tells you how to translate between neighboring clocks. And that field is exactly the one whose variations are the electric and magnetic fields you can measure with a coil or a compass. The payoff becomes clearer in an experiment that seems almost like a magic trick. In the Aharonov-Bohm setup, you send waves of electrons around a region where the magnetic field is confined inside a shielded cylinder, so the electrons never pass through any magnetic pull at their paths. Yet when the two paths recombine, the interference shifts in a way that depends on the hidden flux inside. What changed was not a push along the way, but the bookkeeping of the gauge potential around the loop. A reminder that in quantum mechanics, the potential, the connection that aligns local phase choices, carries physical information even where the field strengths vanish, and loops can detect that hidden twist. Notice how this idea reframes familiar operations engineers already use. Choosing a gauge in electromagnetism, those names like Coulomb or Lorentz, doesn't alter what an antenna radiates or what a scope reads. It only streamlines the bookkeeping by fixing the redundancy in a convenient way, like standardizing all neighborhood clocks to avoid confusion while keeping the ability to compute differences that actually matter. The physics lives in combinations that don't care which gauge you picked, and any good result can be recast in another gauge without changing what a detector sees. Now deepen the view with a gentle generalization. Electromagnetism is the simplest gauge theory, with a single kind of phase freedom that doesn't let different components of the gauge field push on each other directly. But if you imagine a symmetry where the local relabeling has more structure, more ways to rotate your internal arrows point by point, then the connecting field acquires its own self-interactions. And that richer story leads to the kind of binding we attribute to the strong force. You don't need the heavy machinery today, only the insight that local symmetry dictates the form of the interaction, almost like a constitutional law that writes the allowed terms in the equations before any experiment is done. An experiment then fixes only a few numbers, like coupling strengths. This constitutional law carries another gift: insistence on gauge symmetry corrals unphysical degrees of freedom, so they never show up in predictions. The redundancy means some components of the gauge field are pure bookkeeping, not propagating influences, and only the combinations that survive a change of gauge, electric fields, magnetic fields, and loop-based quantities are allowed to affect detectors. This is why textbooks warn you not to confuse the potential's specific value with reality, and also why carefully built measurements that depend on loops or on changes over regions can see subtle, global effects that point-like pushes would miss. Gauge ideas aren't confined to vacuum. In materials, the freedom to redefine phases locally, and the way the connection responds explain phenomena from the shielding of magnetic fields and superconductors to the way waves pick up extra phases when they wander around patterns in a crystal. Here, the gauge field isn't only the familiar electromagnetic one, but can be an effective connection emerging from geometry or order, telling waves how to keep their internal reference straight as they cross complex terrain, which is why modern photonics and electronics talk about synthetic gauge fields engineered by design, rather than discovered in nature. The practical creed you can carry into the lab is simple. When a theory says a certain kind of relabeling changes nothing, try making that relabeling depend on where and when you are. The demand that predictions remain unchanged will force you to introduce a connector field, and its allowed forms will be tightly restricted, often uniquely fixed by the symmetry. Then look for curvatures of that connector, the measurable twists that cannot be gauged away, because those are what push, deflect, and shift phases in devices. Finally, remember that loops and boundaries matter because they reveal information the local field strengths might hide. Let the close be soft and honest. Gauge symmetry sounds abstract until you notice that it is a precise way of stating a modest truth. Some parts of our descriptions are choices, not facts, and that nature, when asked to honor those choices locally, replies by weaving in fields whose patterns are the facts we measure. Forces in this light stop being mysterious agents and become the geometry of how we glue local viewpoints together. And once you feel that shift, circuits, antennas, interferometers, even the quiet deflections in a cloud chamber start to look like different ways of tracing the same underlying promise that redundancy, carefully respected, reveals real structure, Yang-Mills basics, and confinement intuition. If electromagnetism feels like traffic guided by painted lane lines, Yang-Mills theories feel like traffic where the lane lines themselves can move and push back, because the connection that keeps neighboring directions aligned is no longer a single, quiet guide but a family of guides that interact with one another, and that one twist, self-interaction among the force carriers, changes almost everything you learned from simpler fields and leads to the hallmark phenomenon called confinement. To step into this gently, imagine that the charge you're tracking doesn't have just a plus or minus label, but comes with an internal arrow that can point in several allowed ways. And as you walk from place to place, you need a rule for how to compare those internal arrows. A rule provided by a gauge field, just as in electromagnetism. But now, there are multiple components of that field, and rotating your internal arrow in one neighborhood can influence the rule in the next. So the connectors carry charge themselves and can tug on each other, producing a dynamic, knotted field that behaves very differently from light. This self-interaction is the seed of two linked surprises. At short distances, the force becomes shy and lets quarks behave almost like free particles, while at long distances, the force refuses to fade and instead pulls with an almost constant tension, so that trying to separate a quark from its partners is like stretching a tough fiber. Keep pulling, and the energy you invest creates a new quark-antiquark pair from the vacuum, snapping the fiber not by letting it go slack, but by breaking it into two shorter fibers that each end in a bound neutral composite. This is the working picture of confinement, and it explains why no experiment has ever isolated a single quark, even though all modern detectors teem with their bound states. You can develop intuition for why this happens without drowning in symbols by comparing field lines. In electromagnetism, lines of electric fields spread outward and thin with distance, so the force weakens. In a non-Abelian Yang-Mills field, the lines attract and bundle into tubes, narrow strands of energy linking sources, because the field feeds itself and prefers to stay knotted. And a tube with roughly fixed energy per unit length means the farther you try to pull the sources apart, the more energy you store linearly, just like stretching a sturdy string. In high-energy collisions, when quarks fly away, the stretched tubes fracture and hadronize, turning the stored field energy into sprays of new particles that stream out as narrow jets you can see in detectors, a direct experimental echo of the fiber-like fields at work, rather than free, long-lived quarks. The other side of the coin is the short-distance shyness, often called asymptotic freedom, which rests on how the medium of the Yang-Mills vacuum responds. In ordinary materials, electric charges polarize their surroundings in a way that screens them, making the effective charge smaller when you step back. The Yang-Mills vacuum polarizes in a subtler, almost opposite way that enhances the charge when you step back and reduces it when you zoom in. So high-resolution probes find quarks that barely feel each other, while low-resolution views see them locked by persistent strings. This running of the interaction strength with scale has been confirmed across many experiments and is one of the strongest signatures that the theory captures the right physics. Because the carriers interact, the theory also supports excitations made only of the field itself, not quarks at all, bound lumps sometimes called glueballs, and while they mix with ordinary composites in the messy world of real data, their very plausibility follows naturally once you accept that the force can glue itself. Numerically, when physicists put the theory on a grid and simulate it, they see the force between well-separated test charges approach a straight, rising line characteristic of a constant string tension, and they watch large loops in their calculations behave in a way that signals area-dependent suppression, a technical mouthful that simply means big loops are costly because the field forms stretched surfaces, exactly what you'd expect from fiber-like flux tubes. In matter, these ideas surface in patterns you can touch. The spectrum of bound states organizes into families whose masses and spins reflect the tug of these persistent strings. Collisions in colliders produce back-to-back jets whose angular and energy distributions match predictions from string breaking rather than free quark flight. And in extreme conditions, like the early universe or heavy ion collisions, there's evidence the strings can loosen into a fluid of quarks and gluons that flows with remarkably low resistance. Yet even there, when the system cools, confinement reasserts itself and colored objects hide again inside neutral composites, as if the vacuum itself prefers to heal into a phase where the tubes of field reroute and close. It's tempting to file this all under just a different force, but a quiet, deeper lesson sits underneath. Once you insist on a local symmetry with a multi-component internal rotation, the mathematics doesn't politely allow any interaction you want. It dictates the structure of the connection, and therefore dictates that the carriers must interact. From that one structural fact flow the twin behaviors of short-distance freedom and long-distance binding, and those behaviors propagate outward into everything from the stability of atomic nuclei to the angles of jets in high-energy experiments to the properties of the hottest matter humans can create. In practical terms, this means that to predict or design anything in this arena, you ask three questions. What are the allowed internal rotations? How strong is the interaction at the scale you care about? And what boundaries or materials are shaping the field? The closing thought is simple but firm. Yang-Mills theories are not electromagnetism with extra parts. They are a fundamentally richer language where the rules that keep your descriptions consistent become dynamical actors, tying sources together with tubes of energy, teaching quarks to roam freely only at the tiniest scales, and insisting that the colorful interior of matter remains artistically hidden inside neutral shapes. Once you feel that rhythm, self-interaction builds strings, strings bind constituents, and energy in strings births new composites. The once mysterious word, confinement, turns from folklore into a working picture that guides how you read the patterns of the smallest sparks we can make. Path integrals for fields. Functional flavor. What if predicting tomorrow meant listening to every way today could have unfolded and letting those possibilities vote, with some voices loud, some whispers faint, until a single testable answer emerged? That is the path integral view for fields in a sentence, not a parade of symbols, but a principle. To know how a field evolves from a prepared past to a specified future, you consider every continuous movie the field could play in between, and weigh each movie by how economical it is according to a single score called the action. Then you let those weighted movies interfere, reinforcing where they agree and cancelling where they argue, and the result is the probability pattern your detectors will actually see. Begin gently with a path you already trust. In ordinary mechanics, the route a ball takes is the one that makes its action most stationary, which in plain terms is the route that balances pushes and pulls in a neat, Compromise. Tilt the root a hair and the score barely changes. The path integral approach doesn't throw that away. It explains it by saying that in the sum over all possible roots, those near the stationary one contribute with phases that line up, while wild detours contribute out of step and mostly cancel. So the classical path comes out as the loudest chorus when the scale is large and disturbances are gentle. Fields just expand this idea from one object moving along a line to a value assigned at every point in space-time. So a path becomes a full film reel of the field's value everywhere and everywhere between two boundaries. You don't pick a single film, you take them all, and their votes are not equal. Films that wildly violate the field's local rules cancel one another, while films that respect those rules in an average sense build a strong signal. And the sharpest signal of all emerges when you zoom out to scales where many tiny cancellations average away, giving you the familiar, crisp wave equations for light and the tidy field equations engineers and physicists use daily. The magic of this perspective is practical, not mystical. Once you accept that probabilities come from a weighted chorus of entire field histories, you can compute measurable quantities by turning knobs in a well-defined ritual. Prepare the field with certain sources switched on or off. Encode those sources as gentle pushes distributed across the film reel, and then take averages over films using the same action weight. The objects you average are field values at chosen points, and those averages are exactly the correlations that experiments measure as response functions, spectra, and scattering rates. Expand those averages in a series when the pushes are small, and the terms arrange themselves into a pictorial bookkeeping called diagrams, little sketches that summarize who talks to whom and in what order, each one standing for a concrete contribution to the final number you compare with data. Because the weight cares about the whole film, the scheme naturally captures phenomena that are awkward in other languages. A field that needs to borrow energy briefly to explore a classically forbidden region is handled by films that sneak through the barrier but pay a price in the action. So their votes are present but faint and only become audible when you tune circumstances to let them matter. A field that lives on a landscape with several valleys will have films that linger in one valley or hop between them, and the final answer will include interference between these narratives, seeding tiny effects that careful measurements can detect. And fields interacting with thermal environments can be handled by slightly rotating the time axis in this film language, which turns the same machinery into a calculator for equilibrium properties. Suddenly, specific heat, susceptibilities, and spectral lines sit on the same page as scattering amplitudes because they are all averages over ensembles of films. The difference being whether you're averaging in real time or in a clock that has been folded into a loop. The path integral picture also spotlights locality and symmetry with unusual clarity. The score for a film is built from what the field and its immediate neighbors do at each moment, so the weight is a product of many local factors. If your theory respects a certain symmetry, say, the freedom to relabel a phase at each point or to rotate internal color arrows, the weight is constructed so that films differing only by that local relabeling get exactly the same vote. And insisting on this at every point forces the appearance of connector fields whose own films must be included. Now gauge fixing becomes a housekeeping step, choosing one representative film among many, equivalent ones so you don't count the same physical situation, repeatedly without changing the answers that depend only on loops and curvatures that no relabeling can erase. If you're wondering how any of this turns into numbers you can compare to a plot on a screen, the answer is that in many problems the sum over films can be approximated or simulated. When interactions are weak, the dominant contribution comes from films that are small ripples around a stationary solution, and the diagrammatic expansion captures the corrections in a controlled way. When interactions are strong, you can discretize spacetime into a grid. Define a finite set of film frames and let a computer sample them with the proper weight, recovering continuum predictions by shrinking the grid spacing, a brute force method that has mapped the behavior of strongly interacting fields where pencil and paper expansions fail. And when the action has wide, smooth basins that dominate, you can use stationary film estimates, the saddle method, to extract leading behaviors and then compute subtle deviations as small corrections. A technique that explains why classical field equations are so reliable at macroscales and how to calculate the gentle quantum size layered on top. One of the most striking gifts of the film ensemble view is that it unifies storytelling. Scattering in a collider, light leaking through a tiny aperture, signals reflecting in a microwave cavity, and collective oscillations in a cold gas can all be read as particular averages over films with different sources and boundary conditions. Change the boundary, close the mirrors into a box, for instance, and you change which films are allowed to contribute strongly. And the shift in the total vote shows up as a measurable energy difference you might see as a pull between plates, a shift in resonance, or a new pattern in a spectrum. Tune the source so that two families of films that end in the same final state carry opposite phases, and their contributions cancel, reducing a rate that naively should grow. An interference control trick used in precision experiments to suppress backgrounds and reveal delicate effects that would otherwise be lost in noise. If you want a memory, you can carry forward. Let it be this rhythm. Define what is fixed at the beginning and end. Values on a boundary, a pulse in, a measurement rule out. List all films of the field consistent with that setup. Give each film a weight built from a local score that encodes the dynamics and respects the symmetries. Average the observables you care about over that ensemble. Simplify the average by expansion, simulation, or saddle estimates appropriate to the regime. This five-step dance is the engine behind a vast fraction of modern predictions in field theory and in many neighboring areas of physics. Let the close be soft and honest. The path integral for fields is not a mystical invitation to believe in every possibility as equally real. It is a disciplined accounting trick that lets the lawful histories speak with volumes proportional to their internal consistency. In the quiet limit, you hear the classical melody clearly. At finer volumes, you hear harmonies of fluctuation. And in extreme settings, you hear new instruments, hops between valleys, films where connectors twist around holes that add colors you would never have guessed from a single trajectory. And by learning to think in films rather than isolated moves, you train your mind to ask better questions. What are the boundaries? Which symmetries must the score respect? Where do the loud films live? How can I gently retune the setup so the films I want to hear sing out? And those questions, more than any formula, are what make the functional flavor of path integrals a working craft, rather than an abstract slogan. Renormalization group flows on theory space. What if understanding a system didn't mean writing one perfect equation, but learning how its rules change as you zoom, like watching a city from street level, and then from a drone and realizing the traffic laws that matter at one scale fade at another? The renormalization group is that zooming method turned into a science of flows, a way to track how the parameters of a theory, its interaction strengths and allowed patterns, evolve when you systematically blur fine details and keep only the features that a coarser eye can see. And once you accept that no measurement sees infinite detail, the question, what happens when I change the resolution, stops being a nuisance and becomes the central tool for prediction. Begin gently with a picture you already trust. If you average the spins in a magnet over tiny squares instead of looking at each atom, you get a new effective magnet living on a coarser grid. Do that again and again. And every time you redescribe the system in terms of larger chunks, you must also update the numbers that tell you how those chunks talk to each other, how strongly they align, how easily they flip, how they feel their neighbors. Those numbers don't sit still. They flow with the scale, and the renormalization group is the rulebook that tells you where these numbers drift as you zoom out or in. Some directions in this drift matter a lot. Tiny changes grow under zooming and reshape behavior, while others die away, becoming irrelevant ripples that vanish at large scales. That simple sorting gives you a new kind of clarity. Instead of memorizing microscopic mess, you ask which features grow under coarse graining and which features shrink, so you can predict the grand behavior of wildly different materials with the same few numbers. This is why universality near phase transitions is real. Water boiling, magnets losing order, liquid helium turning strange, all share the same large-scale patterns because, under RG zooming, their microscopic differences wash away and their flows land on the same special point in theory space. A fixed point where the rules stop changing under rescaling and the system becomes scale-free. At that point, there is no characteristic length, Fluctuations exist on all sizes, so a snapshot looks self-similar. And the measurable way this self-similarity shows up is through critical exponents, the powers that tell you how quantities like heat capacity, susceptibility, or correlation length blow up or shrink as you tune the system. The miracle is that these exponents depend only on broad features, not on the exact atoms or bonds. So vastly different substances share the same exponents because their RG flows meet at the same fixed point. This zooming logic doesn't stay locked in magnets, gases near liquefaction, mixtures separating at the right concentration. Even certain patterns in biological swarms echo the same mathematics of scale. And in particle physics, the RG gives you another kind of vision. It shows that interaction strengths run with energy, so what looks weak in a low-energy experiment can strengthen in a high-energy collider, and what looks strong up close can soften as you probe at even higher resolution. This running is not hand-waving, but measured fact. Precise studies of how electrons and light interact confirm that the effective coupling changes with the momentum you inject, and in the strong force the running flips sign so that quarks behave almost free at tiny distances, but are locked by string-like fields at larger ones. The RG also teaches decoupling. Heavy degrees of freedom fade from relevance when you explore energies far below their masses, so you don't need the ultimate all-detail theory to describe everyday phenomena. You can build effective field theories that include only the actors that matter at your scale, plus a catalogue of possible additional influences whose coefficients are suppressed. And the RG tells you how those coefficients drift as you slowly widen or narrow your lens. This is why a carefully written low-energy theory remains predictive, even though it is not the final word, and why adding higher-order corrections systematically improves predictions without collapsing under infinities. Historically, RG cured a deep illness. Naive calculations of fluctuations and quantum corrections used to produce diverging answers. But Wilson's insight was to reinterpret those infinities as a signal that you are asking a scale-blind question. The fix is to declare a resolution. Adjust your parameters so that measured quantities stay fixed at that resolution, and then learn how those parameters must slide when you raise or lower the cutoff. Suddenly, renormalization becomes not a patch, but an organizing principle that turns messy sums into controlled flows. Practically, this gives you crisp procedures. You measure a few anchor quantities at a convenient scale. You pick a cutoff matching your experimental resolution, and you tune the theory's bare parameters so those anchors match. Now, by following the RG flow equations, you can predict how other observables change when you alter the scale. And the success or failure of those predictions is a direct test of whether your chosen theory lives on the right trajectory in theory space. Visually, it helps to imagine a landscape with arrows showing how theories drift under zoom. Some regions funnel toward a fixed point, an attractor that explains universality, while others peel away. Separatrices, special ridges, divide behaviors, and crossover happens when your flow spends time near one fixed point before turning toward another, which explains why experiments can show intermediate scaling that mimics one universality class before the true large-scale behavior emerges. Even marginal directions, neither clearly growing nor clearly shrinking, can reveal delicate logarithmic drifts that require long patience to see, a reason why certain systems only betray their true scaling after heroic experimental control. Importantly, the RG mindset changes how you design and read experiments. If you want clean scaling, you build systems where the irrelevant clutter is minimized. You tune close to the critical surface so the correlation length grows, and finite size effects can be managed. And you aim for data collapse by rescaling axes, so curves from different temperatures or sizes fall onto a single master line. When the collapse works, you have likely captured the right exponents and the right fixed point physics. If it fails, you look for hidden relevant variables you forgot to control, or for the fingerprints of crossover masking the asymptotic regime. Let the closing be soft but pointed. The renormalization group is a promise that nature is legible even when you cannot track every atom or every virtual fluctuation, because laws at one scale flow into laws at another in disciplined ways. Once you learn to think in flows, what matters grows, what doesn't fades, and special points organize entire families. You stop chasing microscopic trivia and start asking scale-wise questions that travel from boiling water to quantum materials to high-energy scattering. And in that perspective, there is a calm kind of beauty. Reality becomes a river through theory space, with whirlpools and confluences. And your job, as an observer and maker, is to choose where to step in, measure a few depths, and then follow the current to predictions that hold beyond the details of any single shore. Effective field theories. Truth in layers. If you've ever switched from a street map to a subway diagram and then to a flight chart, you already understand the soul of effective field theories. You don't need one map to show every bolt in a bridge and every jet stream across the sky. You need the right map for the job, drawn at the right scale, with the right features kept and the rest politely blurred. And EFTs turn that common sense into a disciplined science of truth in layers, where the world is described by stacked rulebooks that hand off responsibility as you zoom. Begin gently with a familiar contrast. When you listen to a violin, you don't compute the motion of every air molecule. You treat sound as a smooth wave with a speed, a wavelength, and a set of boundary conditions. And that simplified picture predicts echoes in a hall and notes on a scale with exquisite accuracy, until you push to frequencies where the grain of air matters, and then the wave picture phrase. That is the EFT promise in miniature, a contract that says, within this window of energies and lengths, here are the players and interactions that matter. Outside the window, call a bigger theory. In practice, building such a theory starts with 3 decisions. Set the resolution, list the relevant actors at that resolution, and write the most general list of influences among them that respect the symmetries of the situation. No favoritism, no missing terms because they look ugly. Then rank those influences by how hard they hit as you lower or raise resolution. So leading terms guide the main behavior while higher ranked corrections whisper at the margins, giving you a built-in way to estimate your errors. This ranking, often called power counting, turns messy reality into a controllable expansion. You keep the dominant operators first, add subleading ones if you want finer accuracy, and stop when further terms would change predictions by less than your experimental noise. The result is not a brittle cartoon, but a living calculator whose precision is transparent, because each extra term you include reduces a known slice of your uncertainty. Consider hydrodynamics, the EFT for fluids. Its fields are not molecules but density, velocity and temperature, and its equations, continuity, momentum balance, energy flow, are the most general local statements allowed by conservation laws and symmetries. Viscosity and thermal conductivity appear as next-order corrections, and higher-order terms refine the description of shocks and turbulence on suitable scales. Try to follow a single molecule and you drown. But at room scales, the hydrodynamic EFT predicts pipe flows, weather fronts, and wake patterns with power you can test in a wind tunnel. In solids, effective theories talk in phonons, collective vibrations, not atoms, letting you compute heat capacity curves, sound attenuation, and thermal transport without ever naming a nucleus. In nuclear physics, low-energy interactions among protons and neutrons are organized into a chiral EFT whose leading pieces fix the overall attraction and repulsion, while higher-order terms capture subtleties in three-body forces and spin-dependent effects. In particle physics, beta decays at everyday energies are cleanly described by a 4-Fermion contact rule, the Fermi theory, because the heavier messenger that carries the weak force at short distances can be integrated out, leaving behind a compact instruction set that works beautifully until you fire a high-energy accelerator and see the messenger directly, at which point you upgrade to the fuller electroweak map. Even gravity admits layers. Newton's law is an EFT valid for slow speeds and weak fields, while general relativity takes over when curvature and precision demand it, and a post-Newtonian expansion acts as the bridge for systems like in spiraling neutron stars, where you can stack corrections in a controlled way and compare against gravitational wave data. 2 principles make EFTs honest rather than hand-wavy: symmetry and matching. Symmetry, rotations, translations, charge conjugations, internal relabelings, decides which terms are allowed and which are forbidden, shrinking the space of possibilities from infinite guesswork to a tidy menu. Matching is how you fix numbers on that menu. So the smaller theory agrees with measurements at the handoff scale, ensuring you don't double count or miss a contribution, and once matched, you let renormalization group flow tell you how those numbers slide when you change the resolution, giving consistent predictions across neighboring windows. This way of thinking is also a powerful lie detector. If your data demand an effect that no allowed term can mimic, you've learned that a hidden assumption is wrong, or that a new degree of freedom must be near your window. Historically, such mismatches have pointed to new particles, new phases, and new organizing principles long before direct discovery, because EFTs make gaps in the pattern visible. On the flip side, EFTs warn you when they are breaking. If your fitted coefficients grow wildly, or your expansion parameter is no longer small, if new resonances appear right inside your supposed window, or if the neglected terms are the same size as the ones you kept, the map is telling you to flip the page to a higher resolution atlas. Far from being a failure, that moment is a success of intellectual bookkeeping. You know exactly why you must upgrade and what the first signs of new structure look like. Engineers and experimentalists already exploit EFT logic, often without the name. Antenna designers treat currents on a metal surface rather than electrons in a lattice. Circuit theorists replace microscopic charge motion with lumped elements, resistors, capacitors, inductors, then add parasitic corrections when frequencies rise. Optical physicists trade Maxwell's microscopic detail for refractive indices and susceptibilities, then append nonlinear and dispersion terms to predict harmonic generation and pulse shaping. Materials scientists write continuum elasticity for beams and plates, then fold in gradient corrections to catch size-dependent stiffness in micro-devices. In each case, effective doesn't mean approximate and sloppy. It means structured, improvable, and honest about its range. There is also a deep psychological gift here. EFTs give you permission to stop worshipping ultimate explanations in situations where you don't need them, and to start asking scale-appropriate questions that still carry profound insight. Which symmetries rule this window? What is the small parameter that orders the expansion? How large are the next corrections? And what measurement would most efficiently tell me whether I've crossed a boundary into a new regime? These questions replace anxiety about not knowing the whole truth with the craft of knowing enough truth for the task at hand, plus a roadmap for when and how to refine it. Let the closing be soft but clear. The world is layered, and that is not a compromise. It is a feature that makes understanding possible. Effective field theories are our layered atlases, teaching us to draw only the roads we need, to mark the rivers that matter, to shade in mountains only when they change the journey, and to leave the rest for the next page. When you think this way, predictions stop being brittle, errors become transparent companions rather than enemies, and curiosity learns to climb, one scale at a time, toward a horizon that is always there, inviting but never required, because the map you carry today is already enough to get you where you're going. Spontaneous symmetry breaking, Goldstone modes. Imagine standing in a perfectly circular hall where the instructions say, face any direction you like, and yet the moment the music starts, everyone quietly turns toward one particular wall. No rule changed, but the crowd made a choice. That is the essence of spontaneous symmetry breaking. When the underlying laws treat all options equally, yet the system, left to settle, picks one and thereby creates new, gentle ways to move that weren't there before. Ripples that cost almost no energy, because they slide along the very set of choices the law still allows. And those soft ripples are Goldstone modes. Begin with something you can feel. A pencil balanced on its tip honors full rotational symmetry. Turn the table and nothing about the rule, balance, prefers north over east. But a whisper of disturbance makes it fall, and when it does, it points somewhere definite. The rule stayed symmetric, the outcome did not. In materials, a ferromagnet plays this out at scale. Above a critical temperature, 1,000,000 tiny compass needles point everywhere on average, honoring rotational symmetry. Cooling lets them talk to neighbors and they spontaneously align, choosing a direction. Now because the underlying rule still doesn't prefer any absolute direction. Gently twisting the alignment from place to place costs very little energy. A long wavelength, slow twist is almost free, and that low-energy ripple through the chosen direction is a Goldstone mode you can actually measure as a spin wave in neutron scattering. A crystal is another breaking. The laws of space treat all positions equally, yet atoms cooling from a liquid choose a repeating lattice, breaking continuous translation into a discrete pattern. Now nudge the lattice as a whole, and you get sound, phonons, the Goldstone waves of broken translation symmetry, whose speed and polarization you can read off with ultrasound or X-ray scattering. Superfluids and Bose-Einstein condensates choose a phase, a common rhythm for their quantum wave, breaking a continuous turn the phase freedom and giving rise to a very specific, soft density wave that moves without friction under the right conditions. Those acoustic-like Goldstone ripples explain why even a whisper of flow in liquid helium can persist, why tiny rotations gather into quantized vortices, and why ultra-cold gases support second sound pulses that carry entropy the way ordinary sound carries pressure. The universal lesson under these examples is simple, but deep. When a continuous symmetry of the rules is quietly abandoned by the ground state, the system earns a new kind of motion. You can slide along the valley of equivalent choices, instead of climbing a hill, and that sliding shows up as a collective excitation with vanishingly small energy at long wavelengths. This is why Goldstone modes have dispersions that touch zero at zero momentum, and why they dominate the low temperature behavior of broken symmetry phases. They carry heat efficiently, they set how correlations decay across distance, and they decide which responses blow up or calm down as you tune toward or away from order. You can see the birth of these modes at a phase transition, close to the critical point. Fluctuations swell and the system hesitates. A phenomenon you can watch as critical, slowing down in time-resolved measurements, pass into the ordered phase, and very long, lazy ripples become the cheapest motion, announcing the new rule of the land. Twist me slowly, and I barely complain. And experiments from thin magnetic films to ultra-cold atoms have traced those ripples and matched their speeds to theory. Not all broken symmetries give Goldstones. If you break a discrete symmetry, say, choosing heads or tails rather than any angle on a circle, there is no continuous direction to slide along, so no massless ripple is born. Instead, you get domain walls, boundaries between regions that made different discrete choices. And those walls carry tension you can image directly in ferroelectrics or watch wander under a microscope in alloys and spin ices. The contrast is instructive. Continuous breaking yields soft waves. Discrete breaking yields robust interfaces. There is also the question of who does the breaking and who keeps the score. In some systems, the symmetry is an internal freedom that remains a global bookkeeping rule, and Goldstones roam freely. In others, the symmetry is a local gauge freedom whose bookkeeping fields are dynamical, and then the would-be Goldstone excitations don't appear as independent, massless travelers. They are absorbed to endow the bookkeeping field with heft and directionality. You meet that story in superconductors, where the condensates phase couples to the electromagnetic field, and the result is a magnetic field pushed out of the bulk and photon-like excitations that acquire an effective mass inside the material, giving you a finite penetration depth for fields instead of a free Goldstone wave. Goldstone modes also knit together geometry and defects in beautiful ways. Twist a broken symmetry field around a loop, and you can't always untwist it globally. So the material traps winding in the form of vortices, dislocations, or skyrmions. Topological defects whose presence is protected by the way the order parameter wraps the space of choices. Move such a defect and the surrounding Goldstone sea flows, leading to curious dynamics where a skyrmion can skate across a sample under tiny drives. A possibility people now exploit to write low-energy magnetic memory. Because these soft modes are cheap, they flood low-temperature physics. In low-dimensional systems, they can be so abundant that they destabilize long-range order entirely, replacing perfect alignment with quasi-long-range order where correlations decay as power laws. A subtlety you can actually see in thin superfluid films and 2D magnets where vortices and spin waves duel for control. And these waves matter far beyond the lab bench. In the early universe, fields underwent symmetry breakings as it cooled, seeding relics like cosmic strings or textures in some models, and the associated Goldstone-like excitations would have siphoned energy and left imprints we now hunt in the cosmic microwave background or in gravitational wave backgrounds. Whether those particular relics exist is an empirical question, but the mechanism, cool, choose, ripple, runs through much of nature's architecture. For experimenters and engineers, the practical checklist is clear. Identify the symmetry of the high temperature or high energy phase. Identify the order parameter that becomes non-zero as you cross into order. Look for linearly dispersing modes in scattering or transport, and map how their speed and damping track your control knobs. When your data reveal a soft branch touching zero at the origin, you've likely found a Goldstone mode, and when that branch stiffens or gaps as you add couplings that explicitly break the symmetry, you've watched the mode respond exactly as the symmetry story predicts. Let the closing be calm and honest. Spontaneous symmetry breaking is not a cosmic betrayal of fairness. It's the world choosing a stance so it can move in new, graceful ways. Goldstone modes are the whispering freedoms left intact by that choice, the nearly costless slides along a valley of equivalence. And once you train your eye to see them, in the hiss of sound, in the shimmer of spin waves, in the drifting phase of a superfluid, you start to recognize a pattern under the surface of many phenomena. That order is never just rigidity, it is also the permission to glide along hidden directions. And those glides are where the most delicate, revealing music of matter is played. Higgs mechanism as field medium story. Imagine you're told that empty space isn't empty, but more like a perfectly uniform medium that quietly fills everything, and that moving through this medium is what gives certain particles their heft while leaving others weightless. A story that sounds like science fiction until you realize it is the most down-to-earth way to understand the Higgs mechanism. Not as a tangle of equations, but as a field medium that endows carriers of a broken force with mass, decides which directions of vibration are allowed, and leaves behind a real, detectable ripple, the Higgs boson, that we have already seen in the lab. Begin gently by recalling that a medium can change what waves are possible, and that it can screen or expel fields. Then take one careful step. The Higgs field is a medium that doesn't sit in wires or crystals. It pervades vacuum itself with a steady, non-zero value. And because it couples to specific particles, it changes what free motion means for them, adding a kind of inertia that shows up to us as mass without acting like sticky molasses or friction. There is no drag at steady speed, only a cost to changing the state, which is exactly what mass measures. The core move is this. A certain symmetry that once allowed a family of force carriers to be massless is quietly rearranged by the medium's presence, and the vibrations that would have been free, weightless shuffles of the field now intertwine with the medium's internal directions. The result is that some carriers acquire extra components, longitudinal directions of oscillation, not available to massless waves, and those components make sense only if the carriers carry mass. In plainer words, the medium changes the menu of allowed polarizations, and in doing so, demands a price tag, mass for the carriers that interact with it. You can feel the meaning of this in the weak force. Without the Higgs field, the weak bosons would behave like the photon, zipping along with only 2 sideways vibrations and infinite range. In our world, the medium's ever-present value mixes their internal directions so that 2 of them gain a third, longitudinal vibration, and become heavy, which is why the weak force reaches only across subatomic distances before fading. There, mass limits their influence, while the particular blend that does not couple to the medium remains the photon and stays massless, cruising across the universe with 2 sideways vibrations and a range that never runs out. This field medium picture also resolves a practical puzzle. How do matter particles, electrons, quarks, and their cousins, get their masses without breaking the very symmetries that make the theory consistent? The answer is that the Higgs field offers a lawful handshake whose strength is adjustable for each species, and the medium's steady presence converts those strengths into masses. The stronger the handshake, the heavier the particle, which is why the top quark, gripping the medium the hardest, is so heavy, while the electron, with a delicate handshake, is much lighter. Neutrinos are a special coda here. In the original minimal script, they had no handshake and thus no mass. but nature seems to have granted them a tiny one via an extension of the script. Evidence we read from neutrino oscillations, a reminder that the Higgs story is flexible enough to be refined as data demand. If this still feels abstract, anchor it to experiments. In 2012, both major detectors at the Large Hadron Collider saw a new particle decaying in precise, rare ways into pairs of photons, into 4 leptons via heavy bosons, into pairs of bottom quarks and tau leptons that together sketched the fingerprint of a neutral, spin-zero ripple in the field medium itself. Measuring how often those decays happen has steadily tightened the picture. The new particle behaves like the Higgs boson. Its couplings to other particles scale with their masses as expected, and its own mass sets how stiffly the medium resists being compressed or stretched. Earlier generations had already tested the outlines, indirectly, by measuring how W and Z behave and how virtual effects nudge other processes, and the new resonance close the loop by revealing the medium's audible vibrato. The superconductivity analogy, used carefully, makes a useful bridge without turning into a myth. Inside a superconductor, the electron pairs form a collective state that acts as a medium for electromagnetism, giving light an effective mass inside so magnetic fields can only penetrate a short distance. The Higgs medium does something formally similar in vacuum for the weak carriers, but there are 2 crucial differences you should hold on to. The superconductor is a material with edges and temperature dependence, while the Higgs field is a universal background that is there even in the cold emptiness between galaxies, and the thing gaining mass in a superconductor is not the free photon in empty space, but the electromagnetic field inside the material. Whereas in the Higgs case, the W and Z are heavy everywhere, shaping basic phenomena from radioactive decays to the synthesis of elements in stars. A common misunderstanding says mass comes from the Higgs, as if all inertia were rented from this one field. But that's only partly true. For elementary particles, yes, mass is mostly the Higgs handshake. Yet most of the mass of everyday matter is actually energy stored in the churning fields binding quarks, a storm whose weight owes little to the Higgs. It's a good reminder to treat mass as a layered story, with different contributors at different scales. The medium language also helps you see why gluons stay massless. Their force, which binds quarks, corresponds to a symmetry that the Higgs field does not rearrange directly, so its carriers keep only their sideways vibrations and thus remain weightless in vacuum. Meanwhile, the fact that one mixture of the electroweak carriers skips the handshake and stays massless is not a coincidence, but a design. The combination we call electromagnetism is the symmetry left unbroken by the medium, which is why the photon survives unchanged, while the others gain heft. On the engineering side of experimental physics, the field medium story dictates specific production and decay routes you can draw like subway lines. Smash protons, and the strongest line into the Higgs station runs through heavy matter that can briefly stir the medium and emit a Higgs ripple, or aim at 2 incoming weak carriers that fuse, leaving the medium ringing. Once created, the ripple decays into the heaviest passengers it can manage given its mass budget. 2 heavy bosons if there's room, or pairs like bottom quarks or tau leptons, patterns that let collider teams tag and count Higgs events against a noisy background. Subtle variations in these rates are not mere trivia. They are how we test whether the medium couples exactly as the standard script says, or whether new doors, extra particles or altered handshakes are hiding beyond current reach. Cosmology adds a larger canvas. In the early universe, as everything cooled from a hot symmetric broth, the Higgs medium condensed into its present non-zero state, changing the behavior of particles essentially overnight. Whether that transition was a gentle glide or a sharp, bubble nucleating change matters for ideas like how the matter-antimatter imbalance arose. And while the minimal script suggests a smooth slide, small extensions can make it first order, potentially leaving traces in gravitational waves that future detectors may hear. Even today, the measured Higgs mass, combined with other data, hints that our medium may sit in a long-lived but not absolutely deepest valley, a metastable situation that is safe on cosmic timescales yet philosophically intriguing, a nudge that the story might extend in ways we haven't mapped. Through all of this, keep the misconceptions at bay. The Higgs mechanism is not cosmic friction. It doesn't slow a particle coasting in vacuum. Massless and massive carriers differ not by how hard they try, but by which vibrations the medium permits. And the Higgs boson is not the whole medium, it's a localized ripple, the brief thud you can knock out of that medium the way you can excite a density pulse in water. Useful, because by studying its tone and how it couples, you learn the stiffness and reach of the underlying field. Let the closing be soft and precise. When you think Higgs, think a uniform, ever-present field medium that reshapes the menu of allowed motions for specific particles, gives the weak force its short reach, endows matter particles with mass through lawful handshakes, and leaves behind a real ripple we have measured. In that picture, mass becomes less mysterious and more like a property of how waves move through a background, and the vacuum stops being an empty stage and becomes an active, structured part of the play, quiet, invisible to the eye, but absolutely decisive in setting how the drama of particles and forces unfolds. Topological terms. You're used to laws that care about local, pushes and pulls, change the value here, and the field responds there. But there is a different kind of ingredient you can add to a field theory that barely touches the local equations and yet quietly decides global, measurable things. These are topological terms, bookkeepers for how a configuration wraps, twists or threads through space and time, and they leave fingerprints not by exerting ordinary forces, but by assigning phases and response coefficients that only show up when you consider the whole shape of a process or the presence of boundaries. Begin gently with the idea that two field configurations can look smooth and lawful everywhere and still belong to different wrapping classes, the way two loops on a donut can't be slid into each other without cutting, and that you can count such classes with an integer, a winding number that stays put under any gentle deformation. A topological term is a single line in the action that multiplies that integer by a fixed angle and adds it to the system's ledger, so locally nothing changes. But when you compare two histories that differ by 1 unit of wrapping, their interference picks up a definite phase, and the accumulated effect is as physical as a shift in a fringe pattern or a quantized step in a measurement. This abstract-sounding device becomes concrete in several places at once. In systems that live effectively in 2 dimensions, a topological response, known as a Chern term, gives rise to a current that flows along edges with quantized strength. One of the deep reasons the quantum Hall effect shows such stubborn plateaus that refuse to budge under disorder. The bulk is boring in the sense that no local probe sees a conventional force from this term, but the boundary is alive. Channels that conduct with remarkable precision appear because the mathematics insists that when the interior carries a non-zero topological index, the edge cannot remain featureless, so a protected flow must exist to balance the books. In certain magnets and superfluids, a topological term called the Wess-Zumino-Witten contribution encodes how the order parameter field can wrap around its own space of possibilities, and the price of that wrapping is not energy in the usual sense, but a phase that changes the rules for low-energy motion. It can forbid some seemingly allowed processes, stabilize certain textures, or require that smooth deformations be accompanied by quantized steps in a subtle coordinate. Experiments that probe the dynamics of skyrmions, tiny whirlpools, of spin, or track how spin chains respond to slow twists, sniff out these hidden terms by finding half steps where whole steps were expected, or by seeing modes survive against perturbations that should have gapped them. In 3 spatial dimensions, a term nicknamed Axion electrodynamics can be present in special materials called topological insulators, where the electromagnetic response acquires a new cross-coupling. An applied electric field can induce a slight magnetic polarization and vice versa, with a coefficient that is not arbitrary but pinned to an exact value when certain symmetries are respected. This is not an everyday susceptibility you can dial. It's a topological number, often said to be a theta angle equal to a fixed fraction of a full turn, and its physical echo appears at surfaces where that angle jumps. The boundary hosts metallic states that carry current in a chiral way, and exotic image charges and image currents appear near the interface in geometries that would never arise in ordinary materials. Even the strong force in particle physics admits a topological term, again controlled by a theta angle. that counts how the gauge field winds in four-dimensional spacetime. Locally, the equations don't notice, but globally, processes that differ by 1 unit of winding acquire relative phases, and that would tilt certain symmetries in subtle ways, such as inducing a tiny electric dipole moment for the neutron. The fact that experiments have not seen such a dipole to extreme sensitivity tells us the corresponding angle must be extraordinarily small, a puzzle known as the strong CP problem that has motivated searches for new fields whose dynamics might naturally relax that angle towards zero. If such a field exists, its quanta, hypothesized Axion-like particles, would thread cosmology and might even play a role in dark matter, a striking example of how a topological bookkeeping term in a microscopic theory can radiate implications out to cosmic scales. Topological terms are also the grammar behind quantized pumps and Thule-less motors. When you cycle parameters of a system slowly over a closed loop, you can transport exactly an integer number of charges per cycle, even in the presence of weak impurities, because the transported amount equals a topological index that counts how the loop wraps a space of states. Here again, no local force law begs for integer transport. Yet the global accounting insists on it, and experiments in cold atoms and engineered photonic lattices have measured these integer transfers with beautiful clarity, immune to small disorder in a way normal devices can only dream of. Another way these terms announce themselves is through anomalies and parity quirks. In 2+1 dimensions, adding a Chern-Simons term shifts the relationship between current and field in a way that breaks the equivalence between mirror images, giving rise to currents that know left from right and to edge modes that refuse to be localized by impurities. You can detect this through quantized Hall responses without an external magnetic field, a phenomenon called the quantum anomalous Hall effect that has been observed in carefully magnetized topological films, where an integer conductance survives at temperatures low enough that noise and imperfections cannot drown it. The consistent theme is that topological terms don't care about the microscopic details, rough edges, small impurities, or gentle distortions, so long as the global class doesn't change, which is why the corresponding observables are robust and quantized. This insensitivity turns them into metrological gifts. The Hall plateau becomes a standard of resistance, the quantized pump becomes a standard of transported charge per cycle, and protected edge modes become the backbone of devices that can carry information with reduced backscattering. There is a storytelling bonus too. Topological terms knit together bulk and boundary like two sides of a single coin. A non-trivial term in the bulk action often demands compensating degrees of freedom on the boundary. Chiral edge modes, helical surface states, or fractionalized excitations, so that the total system remains consistent. And this bulk boundary correspondence becomes a design principle for finding new phases. Calculate the topological index in the interior, then go to the edge and listen for the modes the index predicts. From a practical how to spot one standpoint, you don't hunt for topological terms by measuring local differential equations. You look for integral statements, count windings around holes in parameter space, measure quantized responses that persist across disorder, watch for surface or edge states that refuse to gap out unless a symmetry is broken, and check for interference patterns that shift by fixed amounts when you thread a configuration through a non-trivial loop. In materials, you map band structures and compute invariants that label them, then verify the predicted edge conduction. In field theory, you track how Instanton-like events connect vacua with different winding numbers and infer the observable phases they impose on rare processes. Let the closing be soft and sharp at once. Topological terms are like a quiet rhythm section in the band of physical laws, inaudible if you solo a single instrument, but decisive when the ensemble plays a full song. They do not push locally, they count globally. They do not bend trajectories, they fix phases, and by doing so, they turn fragile matter into robust conductors, turn smooth deformations into quantized transports, and turn featureless bogs into boundaries that sing, reminding you that sometimes the most reliable facts in physics are not about forces at a point, but about the integer shape of the space your system dares to explore. Anomalies, symmetry, that fails gracefully, you're taught to trust. Symmetry the way you trust a compass. Point it at a problem and it guides you toward conserved quantities and selection rules. But in the quantum world, there is a delicate twist. Sometimes a symmetry that is perfect in the equations you write on paper refuses to survive the full quantum accounting, not by exploding into nonsense, but by failing in a precise, measurable way. That quiet failure is an anomaly, and learning how it appears, when it is fatal, and when it becomes a feature is one of the most illuminating journeys in modern physics, because it ties experiments to deep consistency checks that theories must pass. Begin gently with the idea of bookkeeping. A classical symmetry says, if you nudge the system along this special direction in its space of possibilities, nothing changes. And from that promise you derive a conservation law, some current that should not leak. Quantization, however, asks you to sum the contributions of infinitely many ripples and fluctuations. And in that sum, a symmetry that looked exact can pick up a tiny but unavoidable leak, a mismatch in the counting that no local counterterm can fix. When that happens to a symmetry that the theory uses only as a global label, nature simply tells you your current isn't perfectly conserved. And here is how much it leaks under these conditions. But when it happens to a symmetry that the theory uses as a gauge, redundancy, the scaffolding that keeps your description consistent, the result is catastrophic, unless the leaks from different particle species cancel exactly. This split is your first practical rule. Global anomalies can teach and constrain. Gauge anomalies must cancel, or the theory cannot make reliable predictions. The cleanest, most famous example lives in the way certain chiral currents behave. Classically, you might expect a left-right difference in a fermion's motion to be preserved, yet quantum loops involving the electromagnetic field steal a fixed amount of that current in the presence of crossed electric and magnetic fields, a theft with two profound echoes, one in particle physics, one in materials science. In particle physics, that axial anomaly explains why a neutral pion decays into two photons far more readily than a naive symmetry count would predict. The amplitude is not a fudge. It is the exact price the quantum vacuum pays for the mismatch in symmetry when you let the electromagnetic field thread the process. And experiments have measured that price to exquisite precision. In condensed matter, crystals that host low-energy electrons behaving like massless, handed fermions, Weyl semimetals, display an anomaly-driven transport effect. Apply a magnetic field and drive current, and carriers of one-handedness are pumped from one energy valley to the other, leading to a characteristic drop in resistance along the field direction. The material becomes a tabletop arena where a high-energy anomaly writes its signature in the volts and amps you can read. The story deepens when you insist that a gauge symmetry remain exact after quantization. The standard model of particle physics passes this test only because the contributions from its quarks and leptons cancel one another in a delicate arithmetic that links charges and colors across families. Had nature chosen a different pattern of charges, the theory would spit out contradictions, probabilities failing to add to one, predictions depending on your gauge-fixing choices, and we would have learned long ago that our starting point was wrong. That we instead see harmonious data is not luck, but evidence that this hidden cancellation is real. There are other, subtler anomalies that constrain model building. An odd number of certain doublets would make a purely mathematical obstruction that renders the quantum theory ill-defined. Insisting such obstructions vanish tells you which combinations of representations you're allowed to use even before you look at data. Anomalies also stitch together bulk and boundary like two halves of a ledger. A surface theory that by itself would have a leaking symmetry can be made consistent only when it lives as the edge of a higher dimensional bulk, whose topological term pours in exactly the missing current. This is anomaly inflow, and it is the reason a quantum Hall fluid must carry chiral edge modes that cannot be erased by gentle disorder. Their very existence is the boundary's way of paying back the bulk's topological accounting. In topological insulators and superconductors, similar inflow protects metallic surfaces or Majorana-like modes at edges, so long as the relevant symmetries are respected, making these states robust enough to survive imperfections that would destroy ordinary surface bands. If you prefer a more formal, but still intuitive view, think about changing variables in the grand path summing procedure. You try to enact the symmetry as a relabeling of all possible field histories, expecting nothing to change. but discover that the volume element you're integrating over picks up a phase, an overall factor that you cannot shake off, which is another way to say the symmetry fails at the quantum level. That failure isn't arbitrary. It is quantized and tied to topological features of the theory's configuration space, which is why anomalies are so rigid and predictive. This rigidity makes them extraordinary detectives, because anomalies cannot be changed by smoothing the details. Any low-energy theory must reproduce the same pattern of symmetry breaking as the high-energy one whose charges and symmetries it inherits, a principle called anomaly matching. It tells you that certain massless modes must exist in the infrared if the ultraviolet theory has a given anomaly, or else that some hidden, confined constituents must conspire to carry the missing current in composite form. Over the decades, this logic has ruled out speculative models and guided others toward the only possibilities that can exist. Even gravity is not immune to the diagnostic power of anomalies. In effectively two-dimensional descriptions near black hole horizons, cancelling a gravitational anomaly at the edge forces an outward flow of energy. One way to derive Hawking radiation is the price of maintaining consistency at the boundary between the near-horizon region and the external universe, and a resting example of how a quantum bookkeeping subtlety becomes a physical wind of particles. In three-dimensional systems, a parity anomaly famously explains why you cannot keep time reversal and charge conjugation in their naive classical form when you try to write a single, handed fermion on a lattice or in a continuum without a compensating bulk term. The fix, again, arrives as a topological contribution in the higher dimensional parent that cancels the edge's misbehavior, making the pair whole. For experimenters, the lesson is refreshingly concrete. To hunt an anomaly, don't look for a force, look for a violation with a pattern. A current that fails to conserve by a set amount in a special field configuration, a decay that sneaks through a doorway a classical rule would close, a surface mode that stubbornly remains gapless because the bulk demands it, a quantized transport coefficient that refuses to budge under disorder. Then check whether the would-be symmetry you thought controlled the system is a necessary gauge redundancy or a merely global label. Let the closing be soft but exact. Anomalies are not mistakes. They are messages that the quantum world sends when our classical symmetries overpromise, and those messages come numerically stamped and experimentally audible. By listening to them, we learn what sets of particles and charges are allowed to coexist, why certain edge states are indestructible, why some decays happen at the rates they do, and why theories that look fine on paper sometimes collapse under the first serious question. In that sense, an anomaly is symmetry failing gracefully, not tearing the fabric of law, but embroidering it with a pattern that tells you how the deep structures of fields, topology, and measurement fit together so that the whole tapestry remains coherent. Vacuum structure. Many minima, real consequences. You're taught to treat empty space like a blank page, but the closer truth is that the page can be printed with several invisible patterns at once, and which pattern the world chooses matters for everything that sits upon it. This is what physicists mean by vacuum structure, a landscape with more than one resting place, sometimes a whole family of them, where each minimum defines its own version of nothing and quietly sets the rules for masses, forces, and the kinds of ripples that can exist. And learning to read that landscape explains phenomena from lab materials to the early universe without resorting to fantasy. Begin gently with a picture that doesn't use math. Imagine a rolling countryside of shallow valleys separated by ridges. A drop of dew will settle in one valley and call it home, but another drop over the hill will settle in a different valley and feel just as content. In field language, the height of the landscape is the energy density stored in a given configuration of the field, and a valley is a vacuum, an arrangement with no push to change. But not all valleys are equal, and not all are absolutely lowest. Some are local minima, cozy but not ultimate. Others are global minima, the true bottom. If the world cools into a local one first, a false vacuum, it can live there for ages because the exit requires a coordinated fluctuation big enough to crest the ridge and roll down the other side. Meanwhile, everything you measure, particle masses, force ranges, types of waves, takes its cues from the valley you're in. not from the abstract rules that cover the entire map. This is not mystical. In crystals, a subtle difference in how atoms choose to arrange can create domains with distinct orientations. In liquid crystals, the nothing can point a different way in neighboring regions. In magnets and ferroelectrics, the aligned state can settle in any of several directions. And at the boundaries where domains meet, you don't find emptiness. You find defects, walls, lines, or points that carry energy and can move, pin, or annihilate. Field theory inherits this logic in vacuum with multiple minima, predicting domain walls between regions that chose differently and line-like or point-like defects, when the space of choices has non-trivial loops and knots. The realism of this picture comes out under a microscope and under a telescope alike. In materials, you can watch walls wander under a drive, feel their pinning in hysteresis loops, and image their textures. In cosmology, if the early universe cooled through a transition with several equivalent vacua, horizon-sized patches could choose independently, and the relic interfaces or strings between them would leave signatures. Extra radiation, gravitational waves, lensing patterns that sky surveys can constrain. We haven't seen large harmful networks, which already tells you something about what kinds of vacuum structures nature likely avoided or how transitions must have proceeded. The idea extends in a quieter way when the minima are not equivalent. A vacuum that is slightly higher in energy is metastable, long-lived, but not forever, and the odds of escape depend sensitively on the barrier's shape and height and on ambient conditions like temperature or cosmic expansion. You don't need formulas to grasp the key point. Small changes in the landscape can change lifetimes by outrageous factors, turning microseconds into longer than the age of the universe. So when you hear that our measured parameters place us in a region that could be long-lived, but not absolutely deepest, that is not a scare story. It is a sober statement that the world might have settled into a valley that is safe on all imaginable timescales, and that safety itself is a clue about the map's contour. Vacuum structure also acts like a hidden dial on what you thought were fixed quantities. When a field has several acceptable resting averages, the chosen value can set the masses of certain particles and the strengths of certain couplings. Shift the resting point and you shift the menu of excitations allowed to you, sometimes dramatically. In model building, this shows up as vacuum alignment, where nearly identical Lagrangians lead to distinct low-energy worlds depending on which minimum the fields pick. In condensed matter language, it's as if the same chemical recipe can crystallize into different phases depending on cooldown history and impurities, leading to altered transport and responses. The global organization of vacua can even be layered. Sometimes the landscape decomposes into separate sectors, labeled by an integer that counts a deep topological feature of the field configuration. Moving between sectors is not like sliding downhill in the same valley, but more like tunneling through a mountain to an adjacent basin. Rare events that accomplish this, known generically as topological transitions, can tilt processes in measurable ways. And in some theories, the combination of a topological label with the usual energy landscape introduces an extra angle-like parameter that affects symmetry properties. The empirical absence of certain symmetry-violating signals in precise experiments then binds that parameter to be tiny, pushing theorists to look for new dynamics that naturally settle it near zero. A case study in how vacuum structure can force the architecture of bigger ideas. Finite temperature and density add fresh chapters. Heat shakes the landscape so ridges lower and valleys flatten, allowing the system to hop between minima that were practically sealed off at low temperature. Pressure and chemical potentials tilt the map as if gravity favored one side, driving transitions that create bubbles of a new vacuum inside the old. The bubbles grow when the free energy gain in their interior outweighs the surface cost of their walls, and the resulting dynamics, nucleation rates, wall speeds, collisions, decide everything from grain sizes in alloys to the spectrum of gravitational waves that a cosmological transition might have sent ringing across space-time. This is predictive, not poetic, because the shapes of the bumps and basins fix the characteristic frequencies and strengths of those waves, giving future detectors a concrete target. Even without heat, noise can come from quantum fluctuations. The system can borrow a finite amount of energy for a short time to explore configurations that start it rolling into another minimum, a process whose odds are negligible unless the barrier is just right. Laboratory analogues abound, chemistry's activated processes, superconducting qubits hopping between wells in a designed potential. And the field theory case follows the same moral. You can design parameters, so an unwanted escape is effectively impossible on relevant timescales. The presence of many minima also shapes selection rules you might not attribute to vacuum at first glance. Certain reactions or decays can be strongly suppressed or entirely forbidden not by an explicit symmetry in the equations of motion, but because the initial and final states live in different basins, and the required path over the ridge is implausible given the energies and couplings available. Conversely, a background that aligns the vacuum in one direction can make processes easy that would be difficult in another alignment. This is a powerful diagnostic in experiments and simulations. Scan parameters and watch for sharp onsets or sudden disappearances of channels, and a guide for engineering materials where phase-controlled pathways are the goal. None of this requires mystical thinking about multiple universes. The moral is practical. Empty is an engineered state with a blueprint, and blueprints can have alternative ground floors. When you plan an experiment, you should ask which valley your system is in, how rough its walls are, what defects its history seeded, and whether a gentle nudge, temperature, strain, fields could move it to a neighboring minimum with a measurably different response. When you design a theory, you should sketch the full map, not just the point you like, and check stability and lifetimes, domain structures, and topological sectors so your predictions survive contact with reality. Let the closing be soft but clear. Vacuum structure is not a footnote. It is the quietly decisive backdrop that tells particles how heavy to be, tells forces how far to reach, tells waves which notes to play, and tells histories which routes are open. Once you learn to see the many minima countryside beneath the stage, glitches in data become signposts, relics in the sky become fossils of past choices, and the word nothing loses its blandness and gains the richer meaning it deserves. A patterned calm that can be chosen in more than one way, with consequences written into everything that follows. Instantons and tunneling in field theory. Suppose you press pause on time not by stopping the world, but by turning the clock face sideways so that motion prefers to settle rather than oscillate under that tilted clock. Certain rare field configurations suddenly stand out as honest, finite bridges between distant arrangements, and when you rotate the clock back to ordinary time, their imprint is what we call tunneling. In field theory, those bridges are instantons, and they explain how a system can slip from one valley of its energy landscape to another, even when no classical path goes over the ridge. A leap accomplished not by cheating, but by paying an exact toll that depends on the shape of the entire route in the sideways time picture. Begin gently by replacing the single particle cartoon you may know, one bead confronting a barrier, with a film in which an entire field rearranges across space. On one side of the barrier, the field rests in a particular pattern. On the other, it rests in a different one. And the question is not which bead sneaks through, but what spatial profile, appearing for a brief choreographed moment, allows the whole configuration to pivot from one resting pattern to the other. The answer is a localized lump in the rotated time world, a compact episode where the field climbs partway up the ridge, rolls across a saddle that only exists in that tilted geometry, and returns down into a new basin, leaving behind no perpetual motion but a lasting change in which vacuum, or which winding class, the system occupies. This sideways time trick is not hand-waving. It converts phases that would cause wild cancellations in our usual sum over histories into real weights that suppress unlikely films in a controlled way, so that the rarest, most efficient bridge dominates the tunneling rate. You can measure the practical truth of this in many arenas where collective coordinates matter. Superconducting circuits that hop between quantized current states, ultra-cold gases nucleating a bubble of a new phase, magnets flipping the direction of a nanodomain at low temperature, and the field theory generalization adds something unique. When the space of allowed configurations has distinct topological sectors labeled by an integer, the instanton carries precisely one unit of that label, and successive events can step the system between sectors that no smooth classical motion connects. The price of such a step is encoded in an action that integrates the field's effort over the entire episode. So tunneling is exponentially rare when the ridge is tall and the route is long, and far more common when symmetries or couplings shape a short, gentle bridge. Critically, this price is not guessed but can be computed once you know the landscape, which is why instanton calculus has predictive power. It yields concrete exponents and prefactors for rates, and those rates organize otherwise mysterious phenomena, like the splitting of nearly degenerate energy levels in periodic landscapes, or the temperature-dependent decay of metastable phases in the early universe. In gauge theories with many vacua related by winding, instantons do more than mediate escape. They let the system explore those sectors and thereby inject effects that would be impossible in a naive classical account. Certain processes that seem forbidden by simple counting become allowed with amplitudes proportional to an instanton factor, and selection rules that hold at everyday energies get softened by rare transitions that thread the deep structure of the configuration space. You will not see such events every afternoon, but their possibility has precise consequences. For example, they influence how symmetry-violating interactions could show up in sensitive experiments, and how early universe dynamics might have tipped delicate imbalances toward the matter-dominated cosmos we inhabit. Because instantons are localized in the rotated time picture, their size becomes a dial. Small ones probe short-distance features of the theory, while large ones feel the broad contours. In some cases, many sizes contribute, and you must sum a dilute gas of events, each rarely overlapping with the next. In others, interactions between instantons and their anti-partners become crucial, leading to paired events that nearly cancel phases, or conversely, to chain-like structures whose cumulative effect reshapes long-distance behavior. Numerical simulations on lattices, where space-time is discretized, literally count these topological lumps, track how their density changes with parameters, and confirm that they drive phenomena like the broadening of certain spectral lines or the screening of currents that would otherwise be conserved. This language also clarifies what tunneling isn't. It is not a particle drilling through rock, not faster than light travel, not a violation of energy accounting. The system pays the toll exactly, but the toll is booked in the sideways time ledger, which suppresses the probability rather than demanding a literal climb. When you rotate back to ordinary time, the event appears as a sudden, spatially extended reconfiguration, the birth of a bubble that grows, the flip of a domain with a characteristic wall thickness, the unwind of a topological knot, and detectors see only before and after, plus any radiation shed as the system relaxes in its new basin. Temperature and environment change the story in ways you can test. Warmth lets the system borrow from a thermal bath and hop over ridges, while deep cold favors the instanton route under the barrier. At intermediate regimes, the two mechanisms compete and interfere, producing crossover curves in decay rates that careful experiments have mapped in Josephson devices and nanomagnets. Coupling to noise blurs the delicate phases that shape the preferred bridge and can suppress quantum routes, teaching engineers how to design environments that either protect or quench tunneling depending on the goal. In more exotic settings, instantons carry charges of their own, fractional quantum numbers, or angular momenta tied to how the field wins, and their presence seeds long-range order in unexpected channels. A gas of such events can lock phases between distant regions, while their absence can protect fragile symmetries that would otherwise succumb. Detecting their fingerprints becomes a matter of reading correlation functions for the telltale, exponential scars that rare bridges leave, or searching for rare bursts whose statistics betray a topological step rather than a mundane fluctuation. For your mental toolbox, keep 3 practical questions. What are the distinct basins or sectors available? What is the most economical bridge in the rotated time geometry? And how do temperature, noise, and boundaries modulate its cost? Answer those and you own the scaling of rates, the size and shape of critical bubbles, and the conditions under which rare events dominate the dynamics. Let the closing be soft but exact. Instantons are the disciplined way fields change their minds, the fleeting, localized episodes that let a system rewrite its background without ever breaking its rules. Tunneling is the observable echo of that rewrite in the time you live in, a reminder that possibility in physics is not binary but weighed, Roots exist in proportion to the elegance of their bridges, and by learning to see those bridges, you replace mystery with craft, predicting when a quiet valley will hold, when it will yield, and what the world will whisper as it slips, just once in a great while, into a new and lasting calm. Holography, fields versus gravity dualities. You're told that two stories about the same world rarely agree word for word, and yet holography invites you to believe something bolder. A complete theory without gravity, living on a lower dimensional boundary, can be fully equivalent to a gravitational theory in a higher dimensional interior, so that calculations you cannot do in one language become straightforward translations in the other. Begin gently by picturing a sealed room whose walls carry all the information about what happens inside. Not a fuzzy summary, but an exact diary. And now, let the diary be a quantum field theory, with many interacting degrees of freedom, while the interior is a curved space-time where gravity is dynamical. Then accept the central promise of holographic duality. Every measurable quantity in the boundary theory has a partner in the bulk and vice versa, with no remainder and no secret extras hiding between. To make this useful rather than mystical, you keep a working dictionary. Boundary operators map to bulk fields. The ordinary distance from the boundary becomes a way to encode resolution or scale in the boundary theory. Turning on a source for a boundary operator corresponds to setting the boundary behavior of the matching bulk field. And correlation functions, those multi-point averages that experiments and simulations report, are obtained from how bulk fields wiggle in response, read off from a gravitational action that, at strong coupling on the boundary, may be approximated by classical geometry, a remarkable economy born of the duality's strong-weak swap. This single dictionary unlocks practical results across regimes that normally frustrate you. The thermal state of the boundary theory is dual to a black hole in the bulk whose temperature is its Hawking temperature. Entropy of that state becomes a geometric quantity proportional to the horizon area. Pressure, energy density, susceptibilities, and conductivities of a messy, strongly interacting plasma can be extracted from quasi-normal modes, damped ringing of the black hole, which you compute by solving wave equations in a curved background and reading off how disturbances decay. Transport coefficients emerge as near-horizon data and universal ratios, like the famous shear viscosity to entropy density approaching a simple constant in a broad class of theories, follow from regularity conditions at the horizon rather than from heroic diagram sums. The duality also translates changes of phase into geometric events. A confinement-deconfinement transition in a gauge theory can appear as a swap between two bulk geometries, one with a black hole, one without, whose free energies cross at a critical temperature, so the latent heat and scaling of the transition become computations of geometric volumes and areas. Order parameters that are hard to define cleanly in the field language become lengths or areas of minimal objects in the bulk. And non-equilibrium relaxation, often opaque in many-body systems, looks like the ring-down of a perturbed black hole, with characteristic timescales governed by quasi-normal frequencies you can tabulate. The boundary to bulk scale map gives you another lever. Renormalization on the boundary, your systematic procedure for integrating out short-distance fluctuations, becomes radial evolution in the bulk, so flowing to the infrared is literally falling inward. Deformations that change couplings correspond to adding matter or potentials that reshape the interior geometry. Fixed points where the theory forgets its microscopic details appear as bulk regions where the geometry becomes scale invariant, often taking the form of a negatively curved throat whose properties encode central charges and other measures of degrees of freedom. And crossover between different scaling regimes shows up as geometries that transition smoothly from one throat to another, giving you a visual, calculable image for how physics changes with energy. To keep your feet on empirical ground, notice that the duality, while born in high-energy contexts, has become a toolkit. Condensed matter theorists build effective holographic models to mimic strange metals with linear resistivity, to capture universal features of quantum critical transport where quasi-particles fail, or to represent systems with emergent particle hole symmetries. Heavy ion physicists use holographic insights to estimate how quickly a quark gluon plasma hydrodynamizes and to interpret low viscosity and collective flow patterns. And quantum information thinkers read the dictionary in reverse, using field theory entanglement to motivate geometric constructs and to design error-correcting codes inspired by how bulk data can be robustly encoded in boundary degrees of freedom. None of this is free of caveats. The best understood versions of the duality involve boundaries with large numbers of fields and special symmetries, living at strong coupling where ordinary perturbation theory fails. Real materials are finite, dirty, and lattice-bound. QCD has its own quirks and scales, yet the point is not to pretend a perfect match, but to strip problems down to their universal, symmetry-driven cores and use geometry as a controlled stand-in for complexity you cannot otherwise tame. If a boundary phenomenon is governed by long-distance universality, the holographic bulk often captures its leading logic, even when the microscopic costume differs. The dictionary scales to dynamics. Time-dependent sources on the boundary become collapsing matter in the bulk. Quantum quenches that suddenly change couplings correspond to shells of energy falling in and forming horizons. The growth of thermal entropy maps to horizon area increasing under classical conditions. And the approach to local equilibrium is the smoothing of bulk perturbations as they are irreversibly swallowed. Each of these statements is precise when you phrase it in correlation functions and response kernels, turning problems of turbulent many-body evolution into questions about waves in curved spacetimes. Holography also reframes puzzles that once seemed orthogonal. Information loss in black hole evaporation, which appears pathological in a purely gravitational calculation, can be seen through the boundary where unitary field evolution is manifest. This encourages a search for bulk mechanisms, scrambling in near-horizon regions, subtle correlations in outgoing radiation that reconcile the two viewpoints, and recent solvable models, though not literal ADS CFT, import the holographic mindset to show how semi-classical gravity hides unitary answers in correlations that are hard to see without the boundary perspective. You should carry a clean checklist for using the duality as a craft. Identify the symmetries and conserved quantities of your boundary problem. Pick a bulk model whose isometries and matter content mirror those symmetries. Impose boundary conditions that encode sources and states. Calculate bulk responses. Geodesic lengths for two-point probes at strong coupling, classical wave solutions for spectral functions, horizon data for transport, and translate back using the dictionary. Then test against scaling laws, sum rules, and experiment where available. When mismatches arise, adjust the bulk content in ways that correspond to adding controlled deformations on the boundary rather than patching ad hoc. Let the close be soft but pointed. Holography is not a claim that the universe is literally a movie projected from its edge in every context. It is a precise statement that, for certain quantum field theories, there exists an exactly equivalent gravitational story, one dimension higher. And that equivalence is powerful because it swaps hard for easy, chaos for geometry, and intractable sums for smooth horizons. Once you accept that, you acquire a new habit of mind. When a problem looks hopeless in the language of particles and fields, ask whether a curve of space-time somewhere already solves it. And while you keep your skepticism tuned and your comparisons honest, you can let the idea slow your thoughts and open them at once. Reality might be telling the same tale twice, and if you learn to read both scripts, the shadows on the wall and the shapes in the room begin to teach each other. ADS, CFT, Entanglement Wedges. Imagine drawing a small arc on the boundary of a curved world and being told that, from just that arc, you are entitled to know not only what happens on the wall, but also everything inside a precise, bowl-shaped region of the bulk that the arc owns. That bowl is the entanglement wedge, and learning how it is carved out and what it guarantees is the cleanest way to see how geometry and quantum information agree to share custody of reality in ADS. CFT. Begin gently. Pick a region A on the boundary theory and ask how entangled it is with the rest. Holography answers by telling you to find a special surface in the bulk, floating away from the boundary yet anchored on the rim of A, whose area equals the entanglement entropy of A. This is the Ryu-Takayanagi prescription, upgraded in time-dependent cases to an extremal surface that need not be minimal at every instant, and refined further at quantum accuracy by replacing pure area with generalized entropy, area plus the ordinary entropy of bulk fields that cross the surface. Now collect every bulk point that can send a light signal to A without crossing that extremal surface, and that can also be reached from A by a light signal without crossing it. The closure of all such points is the entanglement wedge of A, the maximal interior region that A is allowed to reconstruct. This is not a slogan, but an operational promise for any gentle bulk disturbance supported inside that wedge. Think of a small field ripple or a localized excitation. There exists a boundary operator built entirely from degrees of freedom in region A that reproduces the same effect on all experiments accessible to A. The information about the bulk ripple is redundantly encoded in the boundary, and the redundancy is not an accident, but the hallmark of a quantum error-correcting code woven into the duality. You can test the logic by trying to move a bulk operator toward the boundary. As long as you keep its support inside the wedge, you can rewrite it on A without changing any measurable consequences. Shove it outside the wedge and that power disappears, and no longer has the right to decode it. In this light, the difference between the causal wedge and the entanglement wedge is revealing. The latter is typically larger, meaning entanglement, not just causal reach, grants you extra interior knowledge. In practice, this shows up whenever the extremal surface hangs deeper than the causal surface, which happens in many thermal and strongly correlated states, where quantum correlations stitch the bulk more tightly than classical causality alone would allow. The wedge can jump in size when you grow A, a clean phase transition, visible as a sudden switch between competing extremal surfaces. A short arc may own only a shallow cap, but beyond a critical opening angle, the preferred surface leaps across a bottleneck and the wedge swallows a much larger interior, instantly upgrading what A can reconstruct. These geometric entanglement transitions mirror sharp changes in boundary entropy and are close cousins of the page curve physics that governs when subsystems become able to decode hidden information. The code perspective sharpens the picture. Bulk operators supported well inside the wedge, far from its bounding surface, have many boundary reconstructions and so are robust against erasing moderate portions of A, while operators near the edge of the wedge are fragile, losing reconstructability when you trim A slightly. This is precisely how distance and protection are defined in error-correcting codes, and toy models built from tensor networks make the correspondence explicit by drawing a tiling of the bulk where pushing an operator through the network tracks exactly how many boundary qubits you need to retain to keep it decodable. The wedge also underwrites quantitative ties between geometry and multipartite correlations. The entanglement wedge cross-section, the minimal surface that splits the wedge into two parts homologous to boundary subregions, correlates with refined measures of shared quantum structure, such as reflected entropy, and, in many contexts, tracks the cost of purifying mixed boundary states. In simple terms, how thick a geometric bridge you must cut inside the wedge signals how much extra room the boundary needs to faithfully represent the joint structure of two regions. Dynamics fit naturally. When you quench the boundary, suddenly changing couplings or injecting energy, the extremal surface bends and the wedge swells, shrinks, or reshapes in time. Thermalization on the boundary becomes horizon formation and ring down in the bulk, and the growth of boundary entanglement is the outward motion of the extremal surface until it hugs a stationary position near the horizon. Reading off relaxation times reduces to computing quasi-normal modes, while memory of initial conditions lives in the portion of the wedge that remains inaccessible to small subregions until their arcs widen sufficiently. Precision enters through modular flow. The many-body operator that generates infinitesimal reweightings of a density matrix on A has a geometric avatar in the bulk, and a deep relation equates boundary and bulk modular generators restricted to the wedge. That equality ensures that relative entropies, subtle, experiment-friendly measures of distinguishability, match on both sides, providing a non-perturbative consistency check that goes far beyond areas and gives you a recipe for reconstructing certain bulk operators by flowing simple boundary ones for the right modular time. At quantum order, quantum extremal surfaces replace purely classical ones, and the wedge's boundary is set by extremizing the generalized entropy. This upgrade matters in situations with strong bulk entanglement, where including the entropy of interior fields can shift the surface outward or inward by order 1 amounts, altering which degrees of freedom are reconstructible. It also anticipates island phenomena in setups coupled to external baths, where regions that would seem out of reach become part of the wedge of a small boundary, because the generalized entropy prefers to include unexpected interior patches. Subtle, yes, but a straightforward continuation of the same rule. Experimentally, while we cannot place probes into an ADS bulk, the logic is testable in engineered quantum systems. Randomized measurements access boundary entanglement entropies. Programmable tensor network simulators and error-correcting circuits implement versions of wedge reconstruction and demonstrate how deleting part of the boundary leaves bulk information intact until you erase past a threshold. And transport and quench experiments in strange metals exhibit scaling and relaxation patterns that align with geometric predictions extracted from bulk models, giving circumstantial but compelling support that the dictionary organizes real, difficult many-body dynamics. Let the closing be soft and clear. An entanglement wedge is not a metaphor, it is a contract. Choose a boundary region, and the duality hands you exactly the portion of the interior that region controls, bounded by a surface whose area tells you how much information is tied up across the cut. As you widen or reshape your region, the contract updates, sometimes smoothly, sometimes with a sudden click as the preferred surface jumps. And with each update, your right to reconstruct the bulk grows or shrinks in a way that mirrors the rules of quantum error correction rather than naive line of sight. Once you learn to think this way, you stop treating geometry and entanglement as separate subjects and start seeing them as two grammars of the same story, the wall's correlations carving the room's shape, and the room's shape teaching the wall how to remember what matters. Emergent geometry from correlations. Start with a simple provocation. If you woke in a dark room with no ruler, no compass, and no map, but you could ask how strongly each object knew each other, how their motions were correlated over time, could you reconstruct the shape of the room? The surprising testable answer is yes, and that is the working spirit of emergent geometry from correlations. Instead of assuming space first and dynamics second, you let patterns of influence, memory, and shared fluctuations define distances, angles, and even a notion of curvature. Then you read geometry off the tapestry of who talks to whom and how quickly their voices fade. Begin gently by grounding the idea in experiments you already trust. When condensed matter physicists measure a structure factor with scattering, they are really measuring correlations and then inferring periodicities and lengths. When radio astronomers do interferometry, they correlate signals across dishes and extract baselines and sky positions. When machine learning researchers do manifold learning, they replace raw coordinates with a distance inferred from similarity, then recover the hidden shape where the data live. Our claim is a unifying version of these tricks for physical systems. Build a matrix of correlations between degrees of freedom, define a sensible notion of closeness from how those correlations decay, and reconstruct an effective geometry that best explains the web of relationships. Two rules keep this honest. First, locality from decay. In many bodies with short-range interactions, static correlations fall with separation and dynamic correlations spread with a maximal speed. So pairs that forget each other quickly are effectively far, while those that remain tightly linked are near. The precise fall-off, exponential, power law, oscillatory, tells you whether the emergent space is gapped and tight, critical and scale-rich, or patterned by underlying order. Second, time from spread. By watching how a localized shake propagates, you extract cones of influence and their slopes. Those slopes define an operational metric because they set how fast signals move between effective locations. Cold atom labs use exactly this logic. They quench a lattice, measure unequal time correlations across sites, and see light cone-like fronts that betray an emergent speed limit. From the front's geometry and the way it blurs and bends, They infer the dimensionality and connectivity that best fits the data. With those principles, a practical workflow emerges. Collect a set of two-point correlators and responses. Convert them into a similarity graph whose edge weights reflect shared fluctuation strength. Compute diffusion distances by letting a random walk wander on that graph for a short time. The more easily probability flows between two nodes, the closer they are in the emergent space. Then embed the nodes in the smallest dimensional arena where these diffusion distances are well represented. The result is a geometry whose geodesics approximate high probability routes of influence and whose curvature encodes bottlenecks and hubs. This is not a mathematician's parlor trick. It predicts lab observables. In disordered wires, the emergent distance between nearby physical sites can stretch dramatically because correlations are strangled by localization. In strange metals, diffusion distances shrink in a way that mirrors fast relaxation and broad transport, hinting at a geometry with weak bottlenecks. In programmable quantum simulators, one can rewrite the same Hamiltonian on different physical graphs and watch the emergent geometry morph even though the nominal coordinates haven't changed. The true space is the web of couplings and correlations, not the laboratory layout. Go deeper, and you can read curvature from correlation triangles. If 2 points are both tightly correlated to a third, but weakly to each other, you have the hallmark of negative curvature, while 3 strong mutual ties suggest positive curvature. Discrete analogues of Ricci curvature built from flows on graphs quantify this, and their sign predicts how disturbances converge or disperse as they move. Information with direct consequences for stability, scrambling, and control. The same correlation-first lens clarifies phase structure without assuming an underlying lattice. At a critical point, correlations become long-ranged, and the diffusion embedding inflates, regions that were far draw close, revealing an emergent scale-free throat. In gapped phases, distances saturate and the space pinches. Across a transition, the geometry can undergo a sharp topological change, like a handle forming or a bridge collapsing, which shows up as sudden changes in connectivity metrics and in the spectrum of the graph Laplacian that plays the role of an emergent Laplace-Beltrami operator. None of this asks you to banish fields or abandon dynamics. Rather, it offers a dictionary, correlators, distances, response kernels, geodesic propagators, transport coefficients, geometric diffusion constants, and butterfly velocities, local light cone speeds. In systems where this dictionary closes, geometry becomes a compressed description of correlation structure, and questions that were hard in one language become easy in the other. Predicting late-time relaxation becomes computing the lowest non-zero eigenvalues of the graph Laplacian. Identifying fragile links becomes searching for geodesics threading narrow necks. Diagnosing hidden dimensions becomes counting how many principal diffusion directions you actually need to fit the data within experimental noise. There is also a gentle bridge to gravity without repeating earlier stories. In fluids and certain media, long wavelength excitations see an acoustic metric, determined by background flow and compressibility. Sound waves propagate as if space were curved by the medium. So the same. Correlation to geometry translation tells you how to design flows that mimic lenses and horizons. Measure correlations of density fluctuations, reconstruct the metric, and watch waves follow the geodesics you predicted. Tabletop analogues of horizons are built this way, and their correlation fingerprints match the emergent geometry forecast. From an information theory angle, mutual information becomes a ruler. The larger the shared information between subsystems after coarse graining, the shorter the effective distance, and the pattern of mutual information links across scales can be organized into a hierarchical network. Think of a multi-resolution tiling that acts like scaffolding for the geometry. Tensor network ansatzer exploit this to place strongly correlated degrees of freedom near each other in a discrete space, making long-range links rare. And the quality of the network's fit to real correlators is a practical test of how many dimensions and which curvature signs the system prefers. In noisy, open settings, the environment reshapes the map. Correlations now obey balance equations with sinks and sources, so diffusion distances must be defined with loss. The emergent geometry fattens along protected pathways and thins where decoherence pries subsystems apart. Engineers can use this to route quantum information by sculpting correlation landscapes with drives and dissipation, a strategy already visible in waveguide QED and in photonic lattices, where topologically protected edge transport shows up as a narrow, low-resistance corridor in the correlation-derived map. To keep this craft rigorous, you maintain a checklist. Choose correlation observables with clear operational meaning. Fix a time window so you don't mix transient and asymptotic regimes. Build distances from monotonic transforms that respect known bounds. Test embeddings with stress measures and with blind predictions. Probe robustness by adding synthetic noise and seeing whether large-scale features survive. When this program succeeds, you gain a tool that answers practical questions. Where should I place sensors to catch early signals? How can I slow or speed equilibration? What is the minimal model? And when it fails, the failure is diagnostic. Stubborn distortions tell you that your system's space cannot be captured by a smooth, low-dimensional geometry. Perhaps it is fractal-like, or dominated by long-range links that demand a different ansatz. And that in itself is a discovery. Let the close be soft and steady. Geometry, in this view, is not a backdrop, but a story your system tells about itself through its correlations. Measure who listens to whom. Watch how quickly whispers travel and the room's shape appears, not as decoration, but as the most economical language for prediction. The beauty of this approach is that it invites you to build space from evidence, to let distances earn their meaning from shared behavior, and to treat curvature as a compact way of saying where influence focuses or fades. So that even in the dark, with only the music of fluctuations to guide you, you can learn the room by ear and draw a map that works. Lattice gauge theory, simulating the continuum. You learn most about water by cupping it in your hands, not by chasing every molecule. And lattice gauge theory is physics' quiet way of cupping the continuum. You take the endless sweep of space and time and replace it with a fine, regular grid. You keep the sacred rule, gauge symmetry, exact on that grid. And then you let the computer watch fields breathe step by step until the fluid truth of the continuum shows through. Begin gently by picturing space as a mesh of points connected by links. And on each link you store the phase memory that tells you how to compare an internal arrow here with one next door, so that when you march around a tiny square and multiply those memories, any mismatch reveals the field's local twist. This preserves the symmetry that forces create without ever mentioning a coordinate choice. And it is the trick that lets numerical simulations remain faithful, while everything else is approximate. From this humble setup, you can already measure the two signatures that define the deep behavior of a confining force. Draw a big loop on the grid, imagine a heavy source and its partner tracing that loop through time, and watch the average of those link memories around the perimeter. If the average falls like the loop's area, you've discovered a string-like pull that tightens as you separate the sources. Confinement in action. Whereas a mere perimeter fall would signal a force that fades. Shrink the grid spacing and the area law that survives teaches you a physical string tension with real units. A number you can compare to the energy in the jets that rip from collisions. The promise grows as you add matter. Putting fermions on a grid is subtle. So different families of discretizations exist, each with trade-offs among cost, exact symmetries, and how cleanly they approach the continuum, and the community has learned to cross-check them all. Staggered formulations that are cheap and fast, domain wall and overlap choices that keep chiral behavior cleaner at a steeper price, improved variants that cancel leading artifacts so you can trust results at coarser spacings. With these in place, you compute hadron masses from first principles, not by fitting models, but by letting bound states form in the digital vacuum and measuring their slow decay in time. The output is not a cartoon. Numbers for the proton, neutron, and their cousins emerge within percent-level accuracy, and purely gluonic bound states, long theorized, show up as heavy, shy resonances in the same framework. Thermodynamics becomes a movie you can watch. Heat the lattice by shortening the time direction, and you see a transition from a world where strings bind to one, where they melt into a fluid of deconfined constituents. You measure the pressure and energy density across that crossover, and hand an equation of state to the heavy ion community to insert into their hydrodynamic codes. You read screening lengths, susceptibilities, and fluctuations of conserved charges that later appear as fingerprints in collider data. And you track how a subtle symmetry that distinguishes left-handed from right-handed motion is partially restored with temperature, a clue to how microscopic anomalies influence macroscopic behavior in the hottest matter we create. Strong interactions at low temperatures reveal other delicate orders. The pattern of how certain bilinears of matter fields condense is read directly from correlation functions. The emergence or suppression of that pattern across masses and volumes is mapped with finite size scaling, and the connection to spectral properties of a large matrix, the lattice analog of a differential operator, turns eigenvalue histograms into order parameter thermometers. Because the grid is finite, you have to correct for the box you live in, and a beautiful finite volume formalism converts discrete energy levels into real scattering phase shifts, allowing you to infer resonance positions and widths as if you had run a tiny accelerator on your desk. Every number you quote comes with a careful path to the continuum. You simulate at several lattice spacings. You hold the physical volume big enough that your particles do not see the walls. You pick clean reference quantities, reference lengths or masses, so you can express results in real units, and you extrapolate to zero spacing with controlled formulas that include the leading artifacts, your discretization leaves. Uncertainties are not vibes but budgets, statistical noise from Monte Carlo sampling, systematic shifts from finite spacing and volume, and renormalization factors that connect lattice currents to continuum ones, each tracked and shrunk step by step. The Monte Carlo engine that drives all this is importance sampling. You do not try every possible field configuration. You wander through the ones that contribute most, like an expert taster sipping only the vintages near the desired flavor. Clever algorithms, hybrid molecular dynamics to propose big moves, multigrid solvers to invert huge sparse matrices swiftly, deflation techniques to strip out stubborn low modes, and flow-based methods to smooth ultraviolet noise without wrecking long-distance content. Turn years of naive computation into weeks, and modern accelerators move the bottlenecks from memory to math and back again. Not every frontier is friendly. If you try to dial a chemical potential to explore dense matter, the probability weights become complex, and you lose the guidance of importance sampling, the sign problem. So the field has developed detours, simulations at imaginary potential with analytic continuation, clever expansions that remain valid in controlled windows, reweighting schemes that squeeze a little truth from hostile terrains, and entirely new ideas on the horizon that borrow from machine learning to map hard distributions into easier ones. Even in the safer zones, long-range topological lumps can freeze at fine spacings, trapping your sampler in one sector for too long. Open boundary conditions, flow techniques that define a gentler notion of topological charge, and dedicated updates that tunnel between sectors help keep the exploration honest. As the grid spacing shrinks and the box widens, the method becomes a microscope for short-distance structure too. You can probe how momentum and spin are partitioned inside the proton by computing matrix elements of currents boosted on the lattice, and then matching them to continuum definitions, a route that has begun to deliver parton distributions from first principles. You can watch how rare decays proceed by computing the hadronic parts that used to be the largest uncertainty, improving the tests that search for cracks in the standard script, and you can quantify how much different quark flavors contribute to electromagnetic moments and radii, with errors that continue to fall as ensembles grow and algorithms sharpen. Beyond QCD, the same craft surveys new territories. Candidate gauge theories for physics beyond the current model can be stress-tested for whether they confine, walk, or break symmetry in ways compatible with precision bounds. Lower-dimensional cousins teach you what universality to expect at criticality. Non-Abelian gauge theories coupled to Axion-Like fields reveal how topology and dynamics braid, and designer models for quantum simulators can be benchmarked before anyone wires up the experiment. The soft lesson to carry is that discretize does not mean distort beyond recognition. By honoring the key symmetry exactly on the grid, by quantifying and removing artifacts with discipline, and by insisting on cross-checks across methods, lattice gauge theory translates the unreachable continuum into a sequence of reachable computations. The closing thought is calm but firm. You do not give up infinity to do this. You learn to approach it, one smaller spacing, one larger box, one clearer observable at a time, until the numbers you read no longer care about the mesh that birthed them, and the continuum answers settle in your hands, like the water you meant to hold all along. Non-Abelian anyons in field language. You can learn a new kind of identity by watching how something returns from a journey, and in 2 dimensions, the journey is not a simple loop, but a dance. When you carry one excitation around another and come back to where you started, the system can do more than pick up a mere phase. It can come back as a different superposition within a shared space of possibilities. And that is the field language heart of non-Abelian anyons. Excitations whose braiding acts like a matrix on hidden degrees of freedom, so that who you are depends on how you were moved, not just on where you are. Begin gently by contrasting with the familiar cases you already trust. Identical particles in 3 dimensions are either bosons or fermions, and swapping them does nothing or flips a sign. But in a flat world where paths can snake without jumping over one another, exchanges are richer, and the algebra of motions is governed by braids rather than simple swaps, which means that winding world lines around each other implements operations that need not commute, so the order of moves matters in a way that's recorded in the state itself. In field terms, you should picture a low energy phase where ordinary local order parameters fail to distinguish what's going on. No magnet pointing this way or that. But where the vacuum still carries structure, stored not in a pattern at a point, but in how extended operators thread space. A topological gauge theory provides the grammar, and its excitations are defects of that grammar. Punctures whose presence changes the allowed global patterns even far away. Fuse 2 punctures, and you don't just add charges. You open a fusion space, a small Hilbert room of options labeled by which combined topological type they can become. And when you then braid one puncture around another, you apply a unitary rotation inside that room. The space's dimension can be larger than 1, which is precisely the non-Abelian case, and that internal room is where information can hide non-locally. Immune to local pokes because there is no local knob that singles out a direction in that room without involving both punctures at once. The cleanest mental model goes like this. Imagine a fluid or lattice with a protected gap, a calm that resists small excitations, and within it create pairs of vortices or quasi-particles that each carry a topological label. Individually they look identical, but as pairs and triples they span a space of joint states, and transporting one around another enacts a specific, pre-programmed rotation in that space. Do it clockwise, then counterclockwise. And you may not end where you began, because the order of operations encodes a non-commuting algebra. This is no metaphorical magic trick. In certain platforms, paired states of electrons that behave like chiral superconductors, special quantum Hall fillings, engineered wire networks that pin Majorana-like zero modes. The rotation rules are calculable, and they've been distilled into fusion rules and braid rules, a compact field language way to tell experiments what to expect without writing long equations. Why should you care beyond the poetry of motion? Because these rules lead to storage and manipulation of quantum information that is unusually tolerant of noise. The qubit isn't a charge on a capacitor plate, or a spin in a specific dot. It's the shared fusion space of several anyons, and idle errors that nudge one location can't easily rotate the encoded state because accessing that room requires coordinated action on multiple punctures. Braiding becomes a sequence of protected gates executed by moving excitations along designed paths. And the final unitary depends only on the topology of the braids, not on their precise timing or geometry, a gift of insensitivity that ordinary qubits have to fake with heavy error correction. This promise is balanced by honesty. Not every non-Abelian species gives you a complete universal gate set by braiding alone. Some, like the ones tied to Majorana zero modes, need an extra unprotected ingredient to reach arbitrary computations. But even then, the hard parts can be pushed into steps that tolerate calibration, while the delicate steps remain topologically protected. Other species, more exotic to realize, could in principle braid their way to universality with no extra help, a north star that guides materials, searches and device designs. The field theory lens also explains robust signatures that experiments chase. Because the order lives in patterns, not local alignment, you diagnose it through global and boundary phenomena. Ground state degeneracy that depends only on the surface's topology, quantized responses that are pinned by integers and remain steady under weak disorder, and special edge modes whose spectra and thermal transport reflect the same topological bookkeeping as the bulk. Interferometers become the stethoscopes. Route quasi-particles along two paths that enclose a set of localized anyons, then recombine. For abelian anyons, the visibility and phase shift reflect simple fractional charge and braiding phase. For non-Abelian ones, the interference depends on the fusion channel of the enclosed anyons, sometimes turning on and off depending on whether the hidden state allows paths to recombine coherently. So the very presence or absence of fringes acts like a measurement of a non-local bit. In wire networks hosting Majorana-like modes, different tests apply. Parity-protected zero-bias features, fractional Josephson effects with doubled periodicity, and teleportation-like correlations when you couple distant ends through a common superconducting C. None of these alone proves non-Abelian braiding, but together, and under careful control, they carve a road toward the definitive choreography. Exchange operations in T-junctions or networks where the braids can be verified by reading out fusion outcomes repeatedly and statistically, showing that different braid orders produce different final distributions, even when geometries are noisy. The language of fields also tells you what can go wrong, so you can design around it. The protective gap must be large compared to temperature and stray noise, so that stray excitations, poisoning events, don't sneak into the system and secretly braid with your computational anyons. Disorder must be gentle enough that localized imposters don't pin along your paths. Coupling to uncontrolled baths can leak information from the non-local room back into local channels, and the speed of motion must sit in the sweet spot. Slow enough to stay in the ground state manifold, fast enough that drifts and poisoning are unlikely, so device engineers shape potentials and use measurement-assisted protocols to trade motion for adaptively chosen projections that enact the same unitary without literally dragging particles. On the theory side, the dictionary you carry is compact but powerful. A topological effective theory encodes the allowed particle types and their mutual statistics. Line and loop operators act as world-line bookkeepers whose algebra tells you which braids are distinct. Fusion spaces appear as Hilbert spaces attached to collections of punctures. And the edge theory reads like a boundary conformal field theory whose central charge and operator content match bulk data. From these ingredients, you can compute entanglement entropies that include a topological contribution, a constant term that doesn't scale with region size, confirming that the order is global rather than local. You can also derive how ground states split with finite size, and how defects bind zero modes that carry the non-Abelian character even when the bulk is inert. Beyond electronics, the same logic travels. In spin liquids, emergent gauge fields and fractionalized excitations can realize non-Abelian patterns in fully insulating magnets. In photonic and atomic arrays, synthetic gauge fields and engineered interactions simulate the same algebra with light and cold atoms, opening platforms where disorder is low and control is high. And hybrid architectures aim to combine clean anyon creation with long coherence memories, so that the topological operations manipulate states that can then be stored or communicated efficiently. The practical workflow you can trust is straightforward. First, build or identify a phase with a clear gap and the right bulk edge structure. Second, demonstrate hallmark bulk and edge responses that are quantized and robust. Third, implement controlled braids or their measurement-only equivalents, and show that different braid words produce distinct, reproducible transformations on the encoded space. Fourth, stress the system, raise temperature, add disorder, change geometry, to verify that the transformations depend on topology rather than details. And finally, close the loop by benchmarking gate fidelities against noise models that include the realistic villains of quasi-particle poisoning and drift. Let the closing be soft but exact. Non-Abelian anyons are not a legend about particles with quirky personalities. They are field-organized promises that certain two-dimensional phases carry quantum rooms you can enter only by moving punctures around one another in the right order. Inside those rooms, information rests in patterns that space alone can't touch, and motion writes logic in loops rather than in voltages, offering you a way to compute and to probe matter that is slow in pace, clear in principle, and, when realized fully, astonishingly resilient, like a melody that survives the noise because its meaning is woven into the braid rather than into any single note. Chern-Simons theory and braiding. Imagine a field theory that refuses to care about rulers, angles, or the exact shape of a path, only whether one loop threads another, and that, almost by stubbornness alone, turns the act of moving quasi-particles around each other into a crisp arithmetic of phases and matrices. That is the promise of Chern-Simons theory, a topological language in two spatial dimensions, where the gauge field is not a messenger of local pushes, so much as a historian of global entanglements, recording which world lines braided and how many times, then cashing that bookkeeping out as measurable responses at the edge and quantized signatures in the bulk. Begin gently by replacing your usual expectations. Most field theories care about distances because their actions depend on the metric, but a Chern-Simons action is indifferent to stretching and squashing. It depends only on how fields are knotted together, so smooth, deformations that leave the pattern of links intact change nothing about its predictions. That indifference is why the theory computes knot and link data directly, and why its observables, the loop operators that trace the gauge connection around closed paths, respond only to topological features like linking number rather than to the detailed geometry of those loops. In an Abelian version, where the gauge group has a single phase, braiding two charged excitations multiplies the wave function by a phase whose size is fixed by the theory's level. A whole number dial you cannot turn continuously without breaking consistency. Require the theory to remain well-defined when you perform large gauge transformations, global relabelings that wind around the space of configurations, and you discover that this level must be an integer, which is why the Hall conductance in clean quantum Hall states jumps between quantized plateaus instead of sliding. Here, the bulk Chern-Simons term encodes a cross-coupling between electric fields and transverse currents that does not dissipate and that survives disorder because it is protected by topology, not by microscopic perfection. Push into non-Abelian territory and the algebra becomes richer. Now the loop operators carry matrix labels. Their expectation values evaluate celebrated link polynomials. And braiding is no longer a mere phase, but a rotation in a finite dimensional space, tied to how excitations fuse, exchange order matters and sequences. Of braids realize non-commuting operations, precisely the structure that underlies non-Abelian, anyons, and the idea that information can be stored non-locally in fusion spaces and manipulated by moving punctures around one another. The field theory picture keeps this grounded. A non-Abelian Chern-Simons theory at a given level corresponds, at the boundary, to a chiral conformal field theory that carries gapless modes with a fixed central charge. This bulk boundary duet is not decoration, but necessity. Put the topological term in the bulk, and you are forced to host conducting chiral edge channels whose anomalies are cancelled by the bulk inflow, so that global consistency is restored only when edge and interior are treated together. Measure heat or charge transport along that edge, and you read off numbers tied directly to the bulk level and to the content of the gauge group, including a quantized thermal Hall conductance that counts. In effect, how many chiral energy carriers run along the boundary. The topological viewpoint also clarifies flux attachment and statistical transmutation without leaning on heavy symbols. Couple ordinary matter to an Abelian Chern-Simons field, and the field binds a sliver of flux to each particle. Move one composite around another, and the attached flux encodes the braiding phase automatically, turning fermions into anyons or anyons into other species depending on the level. The continuum, metric-free description, and the lattice versions agree on the only thing that matters: the winding history. And that is why interferometry experiments are the right probes. In a Fabry-Perot or Mach-Zehnder geometry built from edge channels, the visibility and phase of the interference fringes shift when localized quasi-particles sit inside the loop, because those silent spectators change the braiding class of the traveling paths. For abelian states, the shift is proportional to the charge and level, while for non-abelian states, the fringe can even vanish and reappear depending on the hidden fusion channel of the enclosed anyons, a striking instance of a global, non-local bit dictating a local signal. Because the theory is topological, you can compute on complicated shapes without anxiety. Place the system on a torus and the ground state degeneracy is fixed by group and level, independent of microscopic disorder. Cut holes or connect handles, and the degeneracy changes predictably, not as a nuisance, but as a resource for encoding information. Adiabatically change the topology by opening and closing constrictions in a device, and you enact controlled transformations in the ground state manifold, effectively performing gates by surgery on space itself. Even the mass of the gauge field in this setting teaches a fresh lesson. The Chern-Simons term gives the gauge connection a gap without relying on a conventional medium that breaks symmetries. There is no oscillating long-range force, only short-range stiffness and global memory. So the bulk stays inert while the edge carries the lively chiral dynamics you measure. This separation is why conductance in the quantum Hall regime is so robust. The bulk cannot absorb low-energy excitations because it is gapped by topology, and only the protected boundary can carry them away. The mathematics reaches out to reality through calibration. You can trust. The same level that pins the coefficient of the topological term fixes the step size in the Hall plateau. The same chiral anomaly cancelled by inflow sets the thermal Hall quantum. The same braiding matrices that appear in the field theory dictate the outcomes of two-path interferometers and the statistics of quasi-particle tunneling events. None of these depend on micrometer-accurate lithography or on crystalline perfection, only on keeping the gap open and the symmetry assumptions intact. You can also see where the theory refuses to be cheated. Try to slide the level off its integer and gauge invariance collapses. Try to close the bulk gap and the edge ceases to be protected. Try to scramble braids faster than the system's adiabatic timescale, and you leak out of the topological sector into noisy excitations. These are not obscure caveats, but design principles that guide experiments toward regimes where the topological signatures are loud. In the lab, that means low temperatures to calm thermal quasi-particles, clean enough samples to keep the mobility high, and device geometries that let you braid or interfere without uncontrolled shortcuts. It means reading not just average currents, but noise and higher moments that betray fractional charge and statistics. It means mapping the edge structure carefully, because reconstruction, extra channels appearing due to interactions, can complicate simple stories unless you account for it with a boundary theory matched to the bulk level. Beyond electronic systems, the same Chern-Simons grammar is being emulated in cold atoms, photonic lattices, and mechanical metamaterials, where artificial gauge fields and engineered couplings reproduce chiral edge transport and bulk gaps that resist disorder. There, braiding and edge flow are orchestrated by light or by patterned motion, making new testbeds where loss and decoherence take different forms, but the topological invariants remain the same. Let the closing be soft and precise. Chern-Simons theory gives you a ruler for two-dimensional worlds that measures not length, but linkage. It turns braids into operations, edges into auditors, and plateaus into signatures that weather imperfection. When you think in its language, you stop worrying about every bump in the road and start asking only whether roads cross, loop, or not, because that alone decides phases, statistics, and transport. And the quiet reward is a kind of durability rare in physics. The confidence that as long as the pattern of threads remains, the numbers you read will hold, telling you that beneath the texture of any real device there is a simple, sturdy story woven from loops, levels, and the art of moving one thing cleanly around another. Quantum electrodynamics in pictures. Picture a language where every interaction between light and charge can be sketched as a little story, lines that travel, meet, and part, so that the hardest quantum calculations reduce to reading comics with very strict grammar. That is the working magic of quantum electrodynamics in pictures, where you trade heavy algebra for diagrams that encode step by step how a charged particle talks to the electromagnetic field, and how those talks add up to the probabilities your detectors record. Begin gently by fixing what a picture means. An external line represents something your apparatus can actually prepare or measure: an incoming electron, an outgoing photon, while an internal line is not a hidden particle zipping through the lab, but a mathematical bridge that carries influence between two events in the calculation. At each meeting point, called a vertex, the charge interacts with light, and the diagram as a whole is one possible history contributing to the quantum amplitude. You do not add probabilities diagram by diagram. You add amplitudes, complex numbers with magnitudes and phases. And only after summing all allowed pictures that respect conservation laws do you take the absolute square to predict a rate or cross-section. This is why interference matters even in particle physics. Two distinct graphs can describe different routes to the same final outcome, and their phases can reinforce or cancel before the squaring step. With that rule in your pocket, classic processes become legible. In elastic electron-electron scattering, one electron tosses a quantum of the field to the other and recoils. Draw this as two straight lines exchanging a wiggly line, and you've captured repulsion by photon exchange without leaning on an outdated billiard ball image. In Compton scattering, an electron and a photon meet and part as an electron and a photon of new energy and direction, and two diagrams exchange the order in which the electron absorbs then emits, or emits then absorbs, must be added because quantum mechanics refuses to privilege a sequence when both are consistent with the endpoints. Change the endpoints and your pictures morph by a rule called crossing. Replace an outgoing particle with its anti-particle incoming, and you redraw the same core interactions as entirely different laboratory reactions. Pair production near a nucleus, for instance, is the same grammar as radiation in reverse. So a handful of building blocks, when rearranged, predict a surprising variety of processes that accelerators confirm. The elegance of these pictures scales. Start with the simplest tree diagrams, no closed loops, just direct exchanges, and you already reproduce many lab results at energies where the electromagnetic coupling is small. Then include loops where a particle interacts with its own field or with a virtual pair flickering in and out inside the diagram, and new, very real effects appear. A loop on an electron line subtly tweaks its magnetic personality, shifting the proportionality between its spin and its magnetic moment beyond the naive value. This anomalous shift has been computed and measured to mind-bending precision, with theory and experiment agreeing to many significant digits. A triumph that tells you the picture language is not just cute, but correct. Loops on the photon line encode vacuum polarization, the idea that the vacuum behaves like a medium in which a field briefly stirs virtual pairs that in turn feed back on the field. Seen in pictures, the wavy line fattens by coupling to an electron-positron bubble, and the net effect is that the effective electromagnetic strength depends on the distance scale of your probe, slightly different at atomic scales than at collider scales, so the fine structure constant is not absolutely constant but runs gently with energy. Another loop-based correction, the self-energy of the electron in an atom nudges energy levels just enough to split lines that would otherwise coincide, producing the Lamb shift that precision spectroscopy reads like a signature. The diagrammatic origin of that split demystifies it. The bound electron is never isolated. It is constantly coupling to and recoupling from the field, and accounting for that activity shifts the level ever so slightly. Diagrams also organize the photons that must be there even when you don't ask for them. Anytime a charged particle accelerates, it radiates, and in calculations that means near duplicate pictures where an extra soft photon is attached to one of the legs. Such photons can be so low in energy that your detector ignores them, yet leaving them out of the sum makes the mathematics misbehave, as if probabilities diverged. The cure is honest and physical, sum inclusively over all outcomes that differ only by these undetectably soft attachments, and the bad pieces cancel between emission and absorption corrections, leaving a finite, measurable prediction. This is why experimentalists design infrared-safe observables and why theorists insist on summing the family of pictures appropriate to an actual measurement rather than an idealized, impossible one. The pictures are guided by symmetry in ways you can feel. The freedom to redefine the electromagnetic potential without changing physics, gauge invariance, forces tight relations among diagrams so that unphysical polarizations of the photon never pollute the answer. If you mishandle the algebra or drop a graph you don't like, a gauge test fails, and the discrepancy alerts you before an experiment does. Conversely, when all required pictures are in play, those checks pass and delicate cancellations occur automatically, a sign that you're calculating properties of real light and real charge rather than artifacts of your notation. When diagrams push beyond their remit and produce integrals that blow up at very short distances, the fix is not a hack, but a calibration called renormalization. You anchor the theory to a small set of measured quantities, an electron mass defined by where a propagator pole sits, a charge defined by a long-distance scattering strength, and you express every intermediate infinity as a redefinition of those anchors. The pictures still carry the structure of quantum fluctuations, but their divergences no longer pretend to be predictions. Instead, they become the reason measured numbers at one scale predict numbers at another. This discipline is the backbone of QED's precision and the reason its few input parameters can explain an enormous range of phenomena. The same picture language handles richness in the real world. Bremsstrahlung, the breaking radiation from a charge skimming a nucleus, appears as a tree diagram with an extra soft photon leg, plus loop corrections that you must include to match data. Pair production in strong fields shows up when the field acts like a sea of soft photons so dense that two pictures, the field emits while the particle absorbs, or vice versa, merge into a single, controllable computation. In materials where electrons move slowly and screening matters, effective interactions can be drawn as resumed chains of polarization bubbles, explaining why light slows in matter and why metals reflect. Throughout, the virtue of pictures is not that they are pretty, but that they factorize complexity. You can read each vertex as a universal interaction, each line as a universal way disturbances propagate, and each diagram as a universal building block whose value can be cached and reused in different processes. This modularity lets large collaborations assemble predictions like careful machinery, checking subparts, comparing intermediate outputs, and tightening uncertainties. It also lets you see patterns, logarithms that repeat across families of graphs, cancellations that recur because of symmetry, so you can resume whole towers of pictures when a particular physical limit, like many soft emissions, would otherwise overwhelm you. The diagrams teach restraint too. Internal lines are not particles you could bottle, they are integrals over possibilities, and calling them virtual particles is tolerable slang, only if you remember that nothing inside a diagram is observed until it reaches the edge. Your apparatus never sees a virtual pair. It sees, for example, a slightly different angular distribution of scattered electrons because the sum overall allowed internal stories subtly reshaped the amplitude before you squared it. If you want a practical checklist for using the picture language as a craft, keep this flow. Define the external states your experiment prepares and measures. List all diagrams at the order of precision your goal demands. Enforce the symmetries that relate them. Regulate, renormalize, and fix your anchor quantities to data. Add the soft and collinear cousins required by your detector's resolution. Then square. Integrate over the phase space your setup can access, and report not just a central number, but an uncertainty that tracks which families of pictures you included and which you left for the next round. Let the close be soft but precise. QED in pictures is not a cartoon of light and charge. It is a disciplined storyboard where each panel carries a rule, and the whole strip predicts the world to dizzying accuracy. Once you learn to read it, you stop imagining forces as pushes at a distance, and start seeing them as the coherent sum of conversations at vertices. You stop searching for secret travelers inside a graph and start trusting the interference that comes from adding their stories. And you gain the quiet confidence that a handful of strokes, lines, waves, and junctions can sketch, with scientific honesty and surprising grace, the way light speaks to matter. Scalar fields in the early universe. Start with a suspicion that refuses to go away. When the universe was young and loud, the most important actors may have been the quietest possible fields, scalars, whose value is just a single number at each point in space and time. Simple enough to fill the cosmos uniformly, yet potent enough that tiny jitters in that value became the seeds of everything textured we see today. To understand their role, you don't need heavy symbols, only a few working pictures. How a smooth scalar can behave like a temporary vacuum energy when it slides slowly. How it can act like pressureless matter when it oscillates. How the expanding background first damps its motion like thick syrup and then lets it ring like a bell. And how quantum restlessness in that field, stretched by expansion, can turn into the frozen ripples that later guide galaxies into place. Begin gently by imagining the young universe as a hot, rapidly growing space with a dominant, almost uniform scalar field rolling across a gentle hill in its potential. If the slope is shallow and the expansion fast, the cosmic friction of expansion keeps the field's roll slow, making its pressure negative and its energy density nearly constant. Exactly the recipe for an episode of accelerated expansion that wipes away initial clutter, cools and smooths the cosmos, and sets a clean slate. But the same field need not always be a source of runaway expansion. Once the slope steepens or the friction eases, the scalar picks up speed, overshoots, and begins to oscillate around the bottom of its potential. Averaged over many cycles, those oscillations behave like a gas of massive, quanta, matter-like rather than vacuum-like. So, the same entity that once powered expansion now feeds the young universe with particles and radiation through its couplings, heating it back up and igniting the familiar hot Big Bang. This handoff is not a footnote. It is the reheating or even preheating chapter, a time when oscillations can pump energy explosively into other fields by resonance, creating a turbulent bath that eventually settles into a more ordinary plasma, and the efficiency and violence of that process decide everything from how many relic particles survive to whether dangerous overproductions are avoided. Quantum fluctuations in a nearly uniform scalar are the next quieter miracle. In every tiny patch, the field jitters by a calculable amount. Expansion stretches those jitters from microscopic to astronomical sizes. And because the field is so uniform, each patch keeps a slightly different time book for when the energy density later converts into radiation and matter. Those timing offsets become real, classical density variations. Small at first, but large enough to be the blueprint for the cosmic microwave background's faint temperature modeling and, later, for the web of galaxies. You don't need equations to remember the logic. Fluctuation, stretch, freeze, and translate into density. And the details, how smooth or skewed the distribution is, whether the ripples are mainly curvature shifts or also carry composition differences. Let precision maps of the sky test which scalar stories are allowed and which are fantasy. Scalar fields can play supporting roles that are just as decisive. A curvaton field, nearly inert during the early accelerated stage, can wake up afterward and deposit its fluctuations into the cosmic soup, changing the pattern of density without rewriting the whole expansion history. Light scalar moduli, common in many high-energy frameworks, can dominate too late if they linger and decay after key milestones. So observations of light element abundances and the precise timing of radiation matter equality tell us such fields must either be heavy enough to vanish early or coupled enough to empty their energy in time. Axion-like scalars, fields whose potential is periodic, can start life misaligned from their minimum and only later begin to oscillate when the cosmic friction eases, behaving as an exceptionally cold and smooth form of matter with tiny self-interactions. Their abundance is set not by thermal freeze-out, but by initial displacement and timing, a mechanism so clean that radio telescopes, laboratory experiments, and stellar cooling observations can all hunt for its fingerprints simultaneously. Phase transitions driven by scalars add another verse. As the universe cools, a scalar's preferred resting value can change from the origin to a ring of possibilities, or between separate minima. If the transition is smooth, the field glides and only the ripple spectrum shifts. If it is first order, islands of the new phase nucleate as bubbles and then collide, stirring the plasma and launching a background of gravitational waves whose peak frequency and shape remember the transition's temperature and violence. Next-generation detectors are tuned to listen for exactly such fossils of early universe scalar drama, and a detection would be a direct confirmation that a scalar's potential was not a featureless bowl, but a contoured landscape that the cosmos crossed with audible consequences. Not every scalar is welcome. A light scalar that talks to ordinary matter with unfiltered strength would mediate new forces we would already have measured. So any candidate that survives must be either heavy, very shy, or cleverly screened. Theorists have invented screening mechanisms, ways a scalar's effective influence dies off in dense environments, yet reappears in the thin intergalactic medium. But astronomical tests of galaxy motion, precision planetary tracking, and laboratory torsion balances are steadily shrinking the space where such ideas can hide. On the flip side, a scalar with a slowly varying energy today is a candidate for dark energy itself, quintessence, whose stiffness and drift could, in principle, be read by charting distances to supernova and the growth of structure with time. If future surveys detect a subtle departure from a strict cosmological constant, a rolling scalar would be the simplest reading. Across all these roles, one organizing principle keeps you from getting lost. A scalar's cosmic behavior is set by three dials: its potential shape, the cosmic friction, and its couplings to other fields. Steep plus strong friction can still give slow motion. Shallow with weak friction yields easy rolling. And once the field oscillates, its average pressure and how quickly it decays follow from the potential shape and the available channels. With just those dials, you can categorize families of models, predict the tilt and texture of primordial ripples, estimate the non-Gaussian fingerprints of interactions, and confront them with sky data that now reach precision at the part in 10,000 level. The discipline is as much about what not to repeat as about what to include. Different scalar roles leave distinct, non-overlapping signatures. An Axion-Like misalignment spectrum differs in small-scale structure from thermally produced cold matter. A curvaton imprint may leave extra composition ripples that the microwave background tries hard to forbid. A first-order transition's gravitational wave chorus has a peaked, modelable shape, unlike the gentle rise from merging black holes. A dark energy scalar must be smooth on galactic scales, yet allow galaxies to form on time. So cross-checks across eras and messengers steadily box in the viable stories. If you want a compact practice kit, carry this 5-step habit. Write down the potential's qualitative shape. Decide whether the early motion is slow roll or rapid oscillation. Track the handoff to radiation by listing couplings and likely resonance channels. Compute the primary imprints, and then delete any model that contradicts the most precise facts first before worrying about the rest. The survivors are not many, and that scarcity is a gift. It means data are already telling us how simple the early universe scalar story must have been. Let the close be soft but clear. Scalar fields in the early universe are not mystical decorations. They are the simplest levers the cosmos can pull. Smooth enough to steer expansion, restless enough to seed structure, versatile enough to change roles as conditions shift. And by listening to the faint patterns they left in the sky and the lab, we continue to turn a minimalist script into a richly evidenced history, one where a single number per point, gently guided, was enough to lay out the scaffolding for all later complexity. Inflaton as a field story. Try telling the origin story of the universe as if it were about one field learning to keep time, and you're already most of the way to the inflaton. You imagine a single, smooth degree of freedom that quietly dominates the early cosmos, not by roaring with heat, but by rolling so slowly that its energy density stays almost steady, turning gravity's usual pull into a gentle push and letting space grow faster than any signal can keep up. And you discover that this clock field leaves behind specific, testable fingerprints that make the tale scientific rather than mythic. You don't need heavy symbols to follow the plot. The inflaton lives on a landscape, a potential that tells it which way is downhill. And the expansion of the universe acts like thick honey on its motion, damping any attempt to sprint. When the slope is shallow compared to the honey's drag, the field creeps. The energy density hardly changes, and the expansion accelerates. Crucially, while this is happening, tiny quantum jitters in the clock get stretched to cosmic size and become long-lived time offsets between different patches, so that when the party ends and the universe reheats, those who left early, who left late differences translate into small differences in density, that later steer matter into the web of galaxies. But a good story makes predictions precise enough to be wrong, and here the Inflaton shines. The spectrum of those seed ripples is almost, but not exactly, scale-free, because the clock isn't perfectly steady. It slows gently over tens of e-folds, and that slow change shows up as a slight tilt in the pattern of temperature spots across the sky, a number you can read from the cosmic microwave background, and now know to be just under 1, a clean, falsifiable success of a slowly rolling clock. The same logic ties the amplitude of the ripples to the rate of expansion during the event, and ties another observable, the ratio of gravity wave. Ripples to density, ripples to how high the Inflaton's landscape sat. A taller plateau means a louder gravity wave background, which would reveal itself as a specific twist pattern in the microwave's polarization. The continued absence of that pattern so far pushes model builders toward gentler slopes and lower plateaus, or toward versions of the story where the clock's fluctuations travel more slowly than light inside the medium, or toward multi-clock variations where several fields share the task. You can learn more from the ripple's shape, not just their size. If a single clock controls the expansion and the ripples move at the usual speed, then 3-point correlations, tiny departures from simple randomness, must be small and obey a simple relation in a specific triangle of momenta. Detect a big signal of the wrong shape, and you've tagged extra ingredients like a reduced sound speed or an interacting companion that jostled the clock. Conversely, a quiet, nearly Gaussian sky with a measured tilt is exactly what a single, smooth Inflaton predicts. Even the flow of time after the sprint tells you about the Inflaton's character. When the slope steepens and the honey thins, the field can no longer creep. It descends, overshoots the bottom, and oscillates. Those oscillations are not decorative. They are the engine that converts the clock's stored energy into a hot bath of ordinary particles. Sometimes this release is gentle, as if the clock decays one quantum at a time. Sometimes it is explosive, a resonant pumping that sprays energy into other fields in a few swings. Either way, the reheat temperature sets which relics the cosmos can make, how magnetic fields might seed, and whether fragile light element predictions survive. So measurements of abundances, neutrino counts, and small-scale structure quietly probe the Inflaton's couplings long after the main act ended. A mature view also strips the story to its essentials with an effective language. Rather than guessing the exact landscape, you describe the inflating phase by its broken symmetry. Time translation is no longer sacred because the clock picks a preferred slicing, and that immediately predicts a universal Goldstone ripple whose dynamics capture any single clock version. In this view, changing the Inflaton's sound speed, allowing mild features in the landscape, or letting heavy fields briefly join the dance all map to controlled deformations that leave specific imprints, oscillations in the power spectrum, distinctive shapes of non-Gaussianity, mild ringing in polarization, that sky maps can hunt without committing to one pretty potential. And if you want to ask hard questions rather than accept a friendly tale, this approach helps there too. Does the clock need exquisitely tuned initial conditions, or do many starting points relax to the slow roll attractor anyway? How big a field range did it traverse? Was it a short shuffle or a marathon across values large compared to the characteristic scale that usually limits field excursions? And if it was a marathon, what protects the landscape's flatness from quantum corrections? Those questions translate into concrete observational handles. Long runs tend to predict potentially detectable gravity waves, while small field jogs do not. Sharp kinks in the landscape create localized oscillations in the sky statistics. Lingering companions produce extra, forbidden flavors of fluctuations that precision data already limits strongly. You can even give the plot an epilogue without drifting into fantasy. In some landscapes, the slow roll never ends everywhere at once. Rare patches keep inflating while others exit, leading to an eternally branching structure that raises deep measure questions and motivates a preference for graceful exit designs where the clock's descent is guaranteed, and global bookkeeping remains sane. Whatever your philosophical appetite, the path to evidence runs through the same narrow gate. Predict new patterns in the sky or in relic particles, and then check. What makes the Inflaton story compelling, rather than merely popular, is its ability to be cornered. It solved old puzzles about unwanted relics and mismatched horizons, not by hand-waving, but by generating specific ripple statistics we can measure. It links a by-now well-measured tilt to the clock's slowness. It links a still elusive polarization pattern to how high the early expansion rate was. It turns small deviations from Gaussianity into direct clues about how smooth the medium was and how many actors were on stage. And it ties the post-inflation temperature to the cosmic production line we test with light elements and the cosmic neutrino background. Dozens of experiments across decades have tightened each of these constraints, pruning once fashionable landscapes in favor of quieter, flatter options. And the next generation will either hear the gravitational whisper of a high plateau or force the story into corners where new mechanisms, reduced sound speed, subtle features, or multi-field entanglements play a role. For you, the takeaway can stay simple and honest. The inflaton is not a miracle particle. It is a roll, a field acting as a clock whose slow, nearly constant energy drove a brief era of accelerated expansion and whose quantum restlessness, stretched and frozen, became the blueprint for structure. Its strengths are its restraint and its predictions. Its open questions are clear enough to aim at, and its future is tethered to data precise enough to say yes or no, which is exactly what you want from a good cosmological story. One that slows your mind, invites reflection, and then hands you concrete clues about how the earliest chapters were written. Axion-like fields and dark hints. Start with a riddle that nature whispers but never spells out. Why is the neutron's electric dipole so tiny that experiments keep coming up empty? And why does the universe act as if a certain knob in the strong force, one that could twist physics toward asymmetry, has been dialed almost exactly to zero? The bold answer proposes not a conspiracy, but a field that dynamically recenters that knob. And its gentle spinning remnant is what we call the axion, with a broader clan of cousins known as Axion-like particles that need not fix the strong force puzzle, yet can still lace the cosmos with subtle, testable effects. Think of an axion as an angular degree of freedom born from a symmetry that is nearly perfect. When that symmetry breaks, the angular mode becomes light, its potential shallow and periodic, and the universe can start life with that angular pointer misaligned. As expansion slows the cosmic friction, the pointer begins to oscillate around its favorite orientation, and those coherent oscillations behave like an extraordinarily cold, diffuse form of matter. No thermal jostling, just a vast, classical wave, making axions and ALPs natural dark matter candidates without invoking exotic collisions or baroque production chains. But the real charm of this proposal is that it trades speculation for multiple doors to evidence. One door is the axion's extremely weak but specific coupling to light. In a magnetic field, axions can convert into photons and back, a reversible alchemy that turns quiet hypotheses into laboratory designs. The haloscope experiments listen for a whisper of power at the axion's mass frequency, as the local dark matter wave converts into radio photons. Helioscope instruments point magnets at the sun, hoping to catch solar axions turning into X-rays. Light shining through walls setups send a laser into a magnetic field, block the beam with a wall, and watch for regenerated light beyond the wall, as some photons become axions and then reconvert. None of these tricks requires speculative astrophysics, just patience, purity, and calibration, and their null results. Carve clean swaths through parameter space while recent upgrades begin to trespass into territories where a QCD axion that solves the strong force knob might actually hide. Another door is stellar cooling. Axions, or ALPs, if they couple even faintly to electrons or photons, provide new channels for stars to leak energy. Observations of white dwarf cooling, red giant brightness thresholds, and neutron star temperatures translate into upper bounds on those couplings. And a few datasets even show mild excess cooling that could be read as a hint. Those systematics keep the jury out. The power of this line of evidence is its complementarity. Where labs struggle, stars are superb calorimeters, and where stars are ambiguous, labs are clean. A third door is cosmic optics. As very high-energy gamma rays traverse intergalactic magnetic domains, Photon ALP oscillations can make the universe appear more transparent than vanilla models predict, a pattern some telescopes have tentatively suggested. Similarly, if a very light ALP field drifts across cosmic time, it can rotate the polarization of ancient light by a tiny, frequency-independent angle, a cosmic birefringence that careful polarization maps can test with ever-improving control of systematics. Neither effect is a smoking gun alone, but taken together, they sketch targets for the next generation of surveys. Then there is structure. Ultralight ALPs with masses around 1022 eV would have de Broglie wavelengths measured in kiloparsecs, making dark matter behave like a gently interfering wave rather than a swarm of particles. Such fuzzy dark matter would naturally smooth the innermost density of dwarf galaxies and suppress tiny halos, potentially easing long-standing small-scale tensions, yet it must thread the needle. Too much smoothing would erase structures we do see. So galaxy kinematics, Lyman alpha forest data, and strong lensing caustics now box in how fuzzy the darkness may be. On the other end, heavier axions act more like familiar cold matter, but can clump into dense mini-clusters, or even self-gravitating axion stars, making rare, dramatic targets for microlensing searches and for radio bursts if such clumps pass through magnetic environments and briefly stimulate conversion. Black holes add a fourth, startling door. A bosonic field like an axion around a spinning black hole can draw energy from the spin through superradiance, populating bound states, the gravitational analog of atomic orbitals, that grow explosively if the Axion-Compton wavelength fits the hole's size. The growth robs the black hole of spin and can source nearly monochromatic gravitational waves. The absence of such waves in current bands and the observed distribution of astrophysical spins already exclude swaths of axion masses, turning black holes into precision spectrometers for new fields that couple only gravitationally. Cosmology keeps the bookkeeping honest. If axions formed via early universe misalignment, their relic density depends on initial angle and on when oscillations began. If they were present during inflation, quantum jitters would imprint isocurvature noise, composition ripples uncorrelated with total density, that the microwave background strongly limits. So viable stories either make the axion heavy during inflation, keep its initial misalignment tiny, or avoid populating it until later. Far from a nuisance, these constraints let sky maps test conditions in eras we cannot hope to recreate. And throughout, the strong CP motivation remains a fixed star. The original QCD axion dynamically relaxes the offending knob towards zero through its coupling to gluons, explaining the neutron's near-perfect alignment while predicting a narrow band of masses and couplings. ALPs relax that tie to the strong force, opening broader possibilities for dark matter, stellar effects, and cosmic signals without solving the strong CP problem themselves. But experiments can tell the two apart by the pattern of couplings they uncover. The practical mindset for navigating this landscape is simple. Chase correlated signatures. If a lab search at a given mass window reports a candidate tone, cross-examine it with stellar cooling bounds and with gamma-ray transparency at the same coupling pattern. If a polarization rotation appears in the sky, check frequency independence and hunt for matching hints in quasar spectra and in the CMB while pushing down instrumental systematics. If mini-cluster encounters are claimed in microlensing, listen for transient radio whispers from axion-photon conversion as independent confirmation. And if superradiance corners a mass range, aim resonant detectors there with urgency. Honest caveats keep ambition in check. Instrument artifacts can fake delicate signals. Plasma effects in astrophysical environments can mimic or mask ALP conversions. And stellar models carry uncertainties that must be marched down in parallel with detector noise. But the diversity of doors is exactly the strength. No single systematic spans all of them. Let the close be soft but concrete. Axion-like fields are not a romantic add-on to cosmology. They are a compact answer to a deep symmetry puzzle that, almost accidentally, offers a graceful dark matter candidate and a suite of crisp, low-energy experiments that any serious program can run. They promise wave-based structure on small scales, polarization footprints across the sky, conversion notes in carefully tuned cavities, cooling patterns in old stars, and spin scars on black holes. And because each hint is tied to a different facet of the same quiet field, the path forward is not to believe more, but to measure better, letting independent clues braid into either a discovery that feels inevitable in hindsight, or a disciplined silence that tells us to look elsewhere. Spinor fields. Why fermions are different. Start with a puzzle you can feel in your bones. Why does matter stack, resist, and remember, while light slips through itself and forgets? The answer lives in the way spinor fields carry identity, a way so unlike waves and scalars that you must adjust your instincts. Fermions are not just particles with a half unit of spin. They are excitations of fields whose algebra forbids sharing and whose very bookkeeping flips signs when you swap labels. And that small algebraic twist changes the architecture of everything from white dwarfs to your laptop's metals to the imbalance of left and right in weak interactions. You can approach this gently by asking how to make a relativistic wave for an electron-like entity that won't predict negative probabilities or runaway energies. The remedy is a set of coupled components, the spinor, that march in step so that time evolution respects a strict balance among them. Pack those components into a field and quantize it. And a second remedy becomes non-negotiable. The operators that create and destroy these excitations must anti-commute, meaning that exchanging their order introduces a minus sign. You might shrug at a sign, but that sign enforces the Pauli principle as a structural law. Try to create two indistinguishable fermions in the same state, and the algebra kills the attempt, and it simultaneously guards causality by preventing unphysical signals from appearing when events are space-like separated. In a path integral view, the same demand arrives dressed differently. To sum over histories of a fermion field without breaking the logic of probability, the field's values must be Grassmann numbers, symbols that anti-commute with each other, ensuring that loops of fermions carry the minus signs experiments insist upon, and that the whole calculation respects spinor statistics without any post hoc patches. You don't need to manipulate these objects yourself to appreciate their purpose. The algebra is the lock that keeps fermionic matter stable and quiet at long distances while allowing the right kind of quantum agitation at short ones. From this algebra flow fingerprints you can touch. Fill available momentum states in a box with spin. 1.2 excitations, and the exclusion principle builds a Fermi sea, a silent occupation up to a sharp surface in momentum space. Push on that sea, and it pushes back, creating degeneracy pressure that supports white dwarfs and neutron stars against collapse. Cool, a normal metal, and its low-energy heat capacity scales not like a gas of soft waves, but like the narrow bandwidth of excitations right at that surface. Even the shape of a metal's response to electric fields, the way currents rise and settle, betrays that only the thin shell of states near the Fermi surface can move without violating exclusion. Spinor fields also carry a directional grammar woven into space-time itself. Their components split into chiral pieces, left and right, that transform differently under mirror flips, and this split has real consequences. For massless fermions, helicity and chirality march together, and nature's weak interactions couple almost exclusively to the left chiral piece, producing the asymmetry every nuclear and particle physicist has learned to respect. Once you allow mass, left and right mix. But the memory of that chiral favoritism shows up in processes from beta decay to neutrino scattering. In materials with strong spin-orbit locking, the same spinor logic writes helical surface modes whose direction is tied to a spinor's internal arrow, making backscattering costly and edges unreasonably good at carrying current. Another difference hides in how spinors define vacuum. For bosonic fields, the ground state is the empty room that welcomes arbitrarily many gentle quanta. For fermions, the ground state is full, a sea of forbidden states. So excitations are necessarily particle hole pairs relative to that fullness. Historically, this led to pictures of negative energy levels, but the modern, cleaner view is simply that quantization chooses anti-commutators, fills each mode once at most, and guarantees that the energy can't be lowered by recklessly adding quanta, because adding is illegal where occupancy is already unity. That single structural rule resolves the stability headaches that haunted early relativistic wave mechanics and predicts something startling but true. the existence of antiparticles, partner excitations with opposite charges and quantum numbers, that appear naturally when you create a hole or flip creation and annihilation in the field's algebra. Nobody had to romanticize them into being. The Spinor field symmetry made them inevitable, and cloud chambers and colliders did the rest. Couple spinors to gauge fields and new facets appear with practical bite. The covariant derivative acts like a careful translator that lets the Spinor talk to electromagnetic or non-Abelian connections without breaking charge conservation or relativity. The resulting currents are not optional. They are the measured flows of electricity and weak isospin, and the consistency of those currents under quantum correction sets hard constraints on which collections of spinors are allowed at all. Famously, certain patterns of left and right chiral spinors suffer anomalies unless arranged to cancel, so whole families of charges and flavors end up locked together by a demand that the quantum theory remains sane. This is not decorative math. It's why your field content looks the way it does, and why speculative extensions are quickly ruled in or out by a handful of triangle diagrams and precision data. Even when interactions are switched off, the Spinor's transformation law leaves a mark that's easy to test. Rotate a single Fermion wave function through a full circle and a relative sign appears, a quiet reminder that a Spinor lives in a representation that is a double cover of the usual rotation group. In the field setting, that sign is harmless. Observables are bilinear and lose it, but its presence is the deep reason antisymmetry is even on the table. In condensed matter, that same algebra shapes topological band structures where pairing and inversion symmetries conspire to protect surface states that are, in essence, spinor modes immune to gentle local perturbations. The thermodynamic story diverges just as sharply. Bosons flock, piling into the lowest state and condensing into macroscopically occupied fields, but fermions queue, filling one by one, producing statistical weights that soften at finite temperature but never let go of the exclusion backbone. From this simple curve flow dozens of everyday predictions: the way metals shine, the Sommerfeld enhancement in low temperature properties, the particular form of low energy scattering near impurities, and the linear in temperature specific heat in a Fermi liquid. When interactions are strong, spinor fields can pair into composite bosons, Cooper pairs, that then do condense, but the parentage never disappears. Break a pair and you fall back into the strict arithmetic of antisymmetric occupancy, a dance between fermionic building blocks, an emergent bosonic order that explains superconductivity's dual nature of rigidity and fragility. Spinor fields also carry memory about discrete symmetries, charge conjugation, parity, time reversal. Richer than their bosonic cousins, each acts differently on the components, and whether a given interaction respects or violates them is not a matter of taste, but a signature recorded in decay patterns, electric dipole searches, and scattering asymmetries. The crispest example is the weak interaction's choice to violate parity maximally for certain spinors, a choice that shows up in the handedness of neutrinos and in the angular distribution of beta decay electrons you can measure with tabletop apparatus. Flip the script to materials, and you meet spin momentum locking that mimics parity choices on a lattice, producing surfaces where electrons moving left have spins locked opposite to those moving right. A direct, device-level echo of the Spinor grammar. If you want a checklist to turn this into a working craft rather than a philosophy seminar, keep 3 steps. When modeling matter, start with spinor fields and anti-commutation, not as an add-on, but as the foundation, because exclusion, stability and causality all hang from that hook. When coupling to forces, impose the correct symmetry translations so currents are conserved and anomalies cancel, letting precision tests prune the implausible. When predicting observables, remember that fermionic responses are set by the Fermi surface and by how interactions reshape it. Calculate how excitations near that surface scatter, pair, or become heavy under symmetry breaking, and you will explain transport, spectra, and thermodynamics without invoking metaphors. Do this, and the conceptual differences aren't just words. They are numbers with units you can check. Let the close be soft but firm. Spinor fields make fermions different because they rewrite the rules of sharing and motion at the most basic level. The algebra refuses duplicates. The symmetry ties left and right in ways that matter. The coupling to forces is tightly scripted, and the statistics reorganize both stars and circuits. Once you learn to see matter as spinor excitations rather than tiny spinning balls, the world's most stubborn facts, why chemistry has structure, why solids have surfaces that conduct in one direction better than the other, why some decays know left from right, why a collapsed star can hold itself up with nothing but quantum crowding. Stop looking coincidental and start reading like the natural consequences of a field that says, quietly but absolutely, no two the same, and everything in order. Majorana versus Dirac in field terms. Ask yourself a disarmingly simple question. When you meet a fermion in the wild, how do you know whether it carries a separate identity from its own antiparticle? And you've stepped into the cleanest divide in the field language. Dirac versus Majorana. Two ways of organizing the same spinogramma that lead to different currents, symmetries, and experimental footprints. Begin gently by picturing a Dirac field as a four-component storyteller with a conserved narrative. Call it charge, lepton number, or simply how many more particles than antiparticles you have, so that creation and annihilation operators come in distinguishable pairs and a global phase rotation of the field is a true symmetry, while a Majorana field is the austere version where the story is written without that global bookmark. The field is its own charge conjugate, neutral by construction, and the would-be number symmetry is absent, not broken by dynamics, but disallowed by the definition itself. This single structural choice cascades into practical consequences you can test. A Dirac mass term ties left-handed and right-handed components together and requires both to exist as independent fields. So gauge symmetries must accommodate both chiralities. Whereas a Majorana mass pairs a spinor with its charge conjugate of the same chirality, and is therefore impossible if the field carries an ordinary gauge charge. Electric charge would forbid it outright. That's why you can write Majorana masses naturally for truly neutral fermions, and why the neutrino, the only neutral fermion in the standard model spectrum, sits at the center of this debate. The difference shows up in currents you can hold in your head. For a Majorana field, the vector current that would count number identically vanishes, so there is no conserved charge to tally, and even its electromagnetic personality is pared down. No ordinary electric or magnetic dipole moments survive in isolation. The only allowed static electromagnetic form factor is an anapole, a toroidal response that couples to the derivative of a field and is notoriously hard to see. By contrast, a Dirac fermion, when neutral overall, like a Dirac neutrino, can still possess transition magnetic moments between flavors, and has a non-vanishing vector current that underlies familiar number conservation and scattering patterns. Degrees of freedom track the same logic. At rest, a free Dirac fermion has four real dynamical components, particle, antiparticle, x, two spin states, while a Majorana fermion has only two, spin up or down of a single self-conjugate species, a halving that matters in cosmology, fewer states to populate in the early plasma, and at colliders, reduced combinatorics and distinct angular distributions. If you let these fields talk to weak interactions, the split sharpens again. A Majorana neutrino allows lepton number violating processes because the line you would draw to distinguish incoming antineutrino from outgoing neutrino is no longer a conserved label. The clean iconic test is neutrinoless double beta decay, where a nucleus emits two electrons with no neutrinos balancing the book. The virtual neutrino is absorbed as itself because there is no separate antiparticle species to forbid the contraction. Observe that decay, and you have proved, in one stroke, that at least one neutrino mass eigenstate is Majorana. Fail to see it down to fantastically small rates, and you push the allowed parameter space toward the Dirac corner or toward Majorana masses so tiny or mixing angles so conspiratorial that the effective rate is buried. Even when both options fit oscillation data, which measure mass differences in mixing, not the particle-antiparticle identity, their parameter counting diverges. A Dirac mixing matrix has one physically meaningful CP-violating phase for three flavors, while the Majorana case adds two more phases that never show up in oscillations but do enter in lepton number violating amplitudes like neutrinoless double beta decay. This is a concrete promise to experiment. CP violation in oscillations tells you about the Dirac-like phase. A signal in LNV processes would also be sensitive to the extra Majorana phases, which can enhance or suppress rates through interference, and the pattern across isotopes would begin to decode them. The collider picture, read in field terms, also separates the two. Produce a heavy neutral fermion that mixes with the charged leptons. And if it is Dirac, lepton number is respected, so same-sign dilepton events are suppressed. If it is Majorana, the heavy neutrino can mediate same-sign channels at measurable rates, because the intermediate line can flip from particle to antiparticle without penalty, a textbook signature that experimentalists chase in multi-lepton final states. Non-observation constrains the mixing patterns, but the logic of the test is robust and model agnostic. The origins of mass add a second diagnostic axis. A Dirac mass for a neutral fermion demands a sterile right-handed partner with no standard model charges and a Yukawa coupling to the Higgs. To make sub-eV neutrino masses this way, the coupling must be microscopically tiny, allowed, but aesthetically stark, whereas a Majorana mass can arise through the seesaw idea, add heavy right-handed states with large Majorana masses and ordinary-sized Yukawa couplings, and when you integrate out the heavy sector, the light neutrinos inherit small Majorana masses automatically. The payoffs are twofold: tiny masses with no extreme small numbers and the possibility of leptogenesis, where CP-violating decays of the heavy states in the early universe create a lepton asymmetry that Sphaleron processes convert into the observed baryon asymmetry, an economy of explanation that Dirac neutrinos cannot readily match because lepton number would remain an exact symmetry. The story spills into materials in a way that repays your patience. In superconductors, the pairing potential mixes particles and holes so thoroughly that the effective low-energy description is Bogolyubov-Deganis, where excitations at special points can be represented by operators that equal their own Hermitian conjugates. Majorana modes in the condensed matter sense. These are not elementary Majorana fields from high-energy physics, but they borrow the same self-conjugate algebra and therefore inherit many of the same symmetry-protected properties, including non-local encoding of quantum information and exotic responses at junctions. Crucially, a superconductor already breaks the global U1 number symmetry down to a parity, so the condensed matter setting naturally favors Majorana-like descriptions, where number is not a faithful label, echoing the field theory insight that a Majorana mass is allowed only when no gauge charge forbids it. Even the way discrete symmetries act distinguishes the two. Charge conjugation takes a Dirac field into a different field, the antiparticle species, and can be paired with parity and time reversal to form distinct invariants. A Majorana field is mapped to itself up to a phase convention, so operators that would have been odd under charge conjugation in the Dirac case may vanish identically. The upshot is a thinner menu of allowed form factors and scattering structures for Majorana fermions, helpful when you design searches for dark matter candidates that could be Majorana. For instance, a Majorana dark matter fermion has vanishing vector coupling to the photon and Z at tree level, which pushes you toward axial and higher multipole interactions and changes how direct detection recoil spectra should look. It's worth pausing on what the two categories do not mean. Majorana does not guarantee non-Abelian braiding or topological protection by itself. That depends on the phase and its symmetries. And Dirac does not mean noisy or uninteresting. The labels tell you about internal bookkeeping, not charisma. What they purchase is clarity about which symmetries exist, which processes are legal, and which observables carry the signal. If you want an operational checklist that keeps the reflection honest, try this. First, ask whether a global or gauged U1 number symmetry is exact. If yes, you are in Dirac territory, and lepton baryon number must be conserved in renormalizable interactions. If no, catalog the leading lepton number violating operators and compute the distinctive channels they open. Second, count degrees of freedom. Halved spectra favor Majorana and shift thermodynamic and production predictions. Third, line up the clean probes, neutrinoless double beta decay for light neutrinos, same sign dileptons and displaced vertices for heavy neutral leptons at colliders, electromagnetic moments and scattering parity for dark matter candidates. and parity-odd interference in precision experiments, where aneuploid versus dipole distinctions matter. Let the close be soft but exact. The Dirac-Majorana fork is not a quibble about naming. It is a choice about whether particle and antiparticle are distinct book entries or the same line read backward. And that choice rewrites conservation laws, trims the list of allowed interactions, and plants unambiguous flags for experiment to chase. Once you see it this way, the question ceases to be abstract and becomes a program. Measure the channels that exist only if number is not sacred. Track the form factors that vanish if self-conjugacy holds, and read the cosmos and the collider together to learn, finally, whether some of the most elusive fermions we know are Dirac storytellers with a conserved count, or Majorana minimalists whose very definition makes the number book close. Effective photonics as field playground. What if, instead of solving field theories on paper, you could stage them, light as your matter, patterned media as your space-time, detectors as your observers, and watch the answers appear in oscilloscopes and cameras? That is the deeper promise of effective photonics as a field playground. Not just to guide beams, but to author dynamics, constraints, and conservation laws you can dial and verify in real time, turning abstraction into an experimental habit. Begin gently with a less traveled path, disorder as a design tool rather than a flaw. By engraving controlled randomness into waveguides or resonator lattices, you don't merely tolerate scattering, you choreograph it, producing Anderson-localized optical modes whose spatial extent, statistics, and sensitivity to tiny index shifts make superb platforms for thresholdless lacing and ultra-fine sensing. Tune the correlation length of the disorder, and you sweep continuously from ballistic transport to diffusive wonder to deep localization, a living phase diagram that you can map by measuring speckle correlations and temporal spread. Step next into the spin of light, not as polarization furniture, but as a field theory dial. Engineer gradients of geometric phase so that the optical spin-orbit interaction becomes programmable, and you will watch the spin Hall effect of light steer right and left-handed components along different geodesics, a photonic analog of chiral transport that you can flip by changing a pattern on a wafer, rather than wiring a magnet. At sub-wavelength scales, those gradients act like synthetic gauge fields that bend trajectories and bias interference without ever touching a real charge, teaching you how far electromagnetism without electrons can go. Now let time join the pattern. Temporally modulated refractive index, time crystals for photons, let you build band gaps in the time domain, redirect energy between frequencies as if they were lattice sites, and break reciprocity cleanly by sequencing phase jumps in time rather than by hauling in ferrites. When you combine temporal and spatial modulation, conservation laws generalize. Quanta move on a space-time lattice with selection rules set by the slope of your modulation, and a handheld spectrum analyzer becomes your field probe for synthetic boosts and drifts. Shift scales and light turns into a tool for thermodynamic fields, deliberately shape the optical density of states in the near field, using nanoscale gaps and high Q surface, resonances, and you reshape radiative heat flow with the same clarity that a potential reshapes particle currents. A hot surface then emits at targeted bands and directions. Kirchhoff's law becomes a design equation, and near-field energy exchange beats blackbody limits to enable wafer-scale thermal diodes and heat engines whose working fluid is the photon field. You can measure the equations of state of this radiative fluid by calorimetry and FTIR, watching emission lobes swing as you adjust geometry the way a theorist tunes a coupling. Bring noise into the story, and for once, don't apologize. Treat spontaneous emission and technical jitter as stochastic fields. Harvest them with balanced homodyne, and you can distill squeeze states that press below shot noise, converting randomness into metrological advantage. The degree of squeezing becomes a field strength you can transport through interferometers, and its degradation under loss reads like a renormalization flow. You can quantify with nothing more than phase scans and histograms. Keep the quantum thread and you reach circuit-level field tests. On-chip heralded sources feed reconfigurable interferometer meshes to create and interfere multiphoton states, whose correlations obey some rules derived from unitarity and causality. Violate a rule and you've learned exactly which loss channel or phase drift broke your effective theory. satisfy it across hours and temperatures, and you've demonstrated that your synthetic field really does conserve what you claimed. For dynamics, delay lines and feedback loops let you write integral differential laws directly in hardware. Route light through programmable delays, mix it with its own past, and measure outputs that implement kernels equivalent to memory terms in non-local field equations. Vary the delay spectrum, and you emulate fractional derivatives, viscoelastic responses, and aging models, then validate by comparing measured impulse responses against Laplace domain predictions. With a few meters of fiber and a handful of modulators, you can prototype retardation effects that would be painful to test in matter. Where experiment meets modeling, photonics teaches rigor. Rather than lean on all-seeing simulations, you build digital twins that share the same reduced coupled mode models you would teach in class. Then you pin their parameters from measured pole positions and residues, not from guessed indices and drawings. Heaters, taps, and on-chip monitors close the loop so that the device continuously self-identifies its own effective Hamiltonian. No unknown drift, just updated coefficients. An honesty check most theories never enjoy. Cross-domain couplings push the playground further. In hybrid stacks, magnons in a ferromagnet, phonons in a membrane, and microwave photons in a superconducting resonator all couple to an optical mode. Bias a single variable and you see sidebands shift across 3 energy domains at once, a direct visual lesson in how multi-field interactions reroute flow. Bidirectional microwave optical conversion then stops being a buzzword and becomes a field theory exercise in impedance matching between distinct vacua, with added gain acting like a tunable source term whose backaction you can hear in the noise spectrum. For imaging, treat a multimode fiber as a configurable random medium and invert it like a field equation with unknown coefficients. Learn its transmission operator once, and you gain a programmable propagator that can focus through bends and twists, implement unitary transforms on the fly, and reconstruct scenes hidden behind diffusers by solving an inverse problem whose regularizer is your prior on the field. This is not metaphor. Calibrated fibers already perform microscopes in a hair, and each calibration is a statement about the completeness of your effective basis. Even the curriculum of causality becomes tangible. Kramer's Kronig relations, so often taught as abstract integrals, turn into bench tests, measure amplitude responses of a resonator family, compute the implied phase by Hilbert transform, and watch prediction match interferometry to within the noise floor. Introduce a deliberate non-minimum phase element, and the mismatch flags exactly which pole zero conspiracy you added. A tactile demonstration that analytic structure is not negotiable. The engineering discipline that keeps all this honest is mundane and profound at once. You stabilize temperature and polarization because symmetries deserve steady backgrounds. You package with low hysteresis materials because repeatability is a physical requirement, not a managerial one. You train in situ by letting the device compute its own gradients. Perturb a phase by a dither, read the sign of improvement at the output, and climb the performance hill without ever building a giant model of the terrain. And when you publish, you include blind predictions so the claim effective means more than we got lucky. Let the closing be soft but pointed. Effective photonics is not only a way to route light, it is a studio for writing and testing field laws at human timescales. You sketch a symmetry or a coupling. You etch or modulate the medium that enforces it, and you watch a beam confirm or contradict you with numbers, spectra, and images. Done well, this practice slows the mind, because the device forgives no hand-waving and awakens thought, because each knob is a hypothesis you can try before lunch until field theory feels less like distant mathematics and more like an instrument you can tune, one resonance, one noise budget, one carefully shaped pattern at a time. Open quantum fields, baths and noise. Begin from a place you know well. The moment you stop pretending a system is alone and admit that it breathes the same air as everything else, the rules change. And for quantum fields, that admission is not a nuisance but a doorway, because open fields coupled to baths and threaded by noise let you see how coherence drains, how fluctuations feed dynamics, and how real experiments should be read. Start gently by picturing a field whose gentle ripples live in a world full of other excitations. Phonons, photons, spin waves, or simply the short wavelength parts of the field you don't track. And imagine you keep only the degrees of freedom you care about while you average over the rest. What returns is not a closed equation of motion, but a law with memory and a companion of randomness. A friction kernel that tells you how past motion drags on the present, and a noise kernel that shakes the system in a way that is not white hiss, but colored, structured, and temperature dependent. The surprise, and the anchor, is that these two kernels are tied by a fluctuation-dissipation relation whenever the bath sits in equilibrium. So the same couplings that sap energy also determine the spectrum of the kicks you receive. A compact statement that keeps models honest and aligns calculation with measurement. Move from picture to practice by naming the choices you face. If the bath forgets quickly compared to the system, the reduced state evolves with local in time rules, and you can write a master equation whose coefficients are positive and trace-preserving, so probabilities remain probabilities. Beyond that easy limit lie non-Markovian arenas where the environment keeps a memory and feeds it back, producing revivals, delayed friction, and noise with long tails that you can see directly in correlation measurements. In both cases, the labels you attach to couplings, ohmic, subohmic, or super-ohmic, are not jargon, but fingerprints of the bath's spectral density, telling you whether low, mid, or high frequencies dominate dissipation, and what kind of drift and diffusion you should expect in phase space. The open field stance clarifies decoherence without mystique. Pick a basis of coarse configurations, nearly classical field shapes over some region, and ask how quickly superpositions between different shapes lose visibility. The answer scales with how loudly those alternatives talk to the bath. Large separations in configuration space or strong couplings let the environment read you quickly, so the interference fringes smear on short timescales. Small separations linger, and if the noise is structured, say, gapped or narrowband, you can even protect specific patterns that align with the bath's def spots, a design principle used in metamaterials and superconducting circuits to shelter delicate modes. The same language demystifies stochastic dynamics. Integrate out the bath, and you get effective equations that look like Langevin laws for fields, damped wave equations stirred by random sources whose statistics you can measure. Average over the noise, and you reproduce dissipative evolution. Condition on specific noise realizations, and you generate synthetic trajectories whose ensemble explains line shapes, switching rates, and spectral diffusion. In driven platforms, this perspective becomes predictive engineering. Shape the impedance seen by a microwave mode, and you sculpt both its damping and its quantum noise. Place a mechanical membrane in an optical cavity, and radiation pressure shot noise, and dynamical back action. Set cooling limits and instability thresholds you can read off from response functions that any spectrum analyzer can capture. None of this requires you to abandon relativity where it matters. For quantum fields near horizons or accelerated detectors, the bath can be the vacuum itself, whose fluctuations look thermal when sampled along specific world lines. An operational reminder that noise is as much about how you probe as about what is really there. In expanding backgrounds, the environment can be the inaccessible modes beyond a causal boundary, and tracing them out gives the long modes an effective temperature and a drift that alter how correlations grow. A clean route to estimates of decoherence for large-scale structures that avoids fairy tales and sticks to kernels you can compute. In matter, open field thinking is the daily craft. Magnons damp by shedding momentum into phonons. Exciton polaritons in microcavities inherit noise from both light leakage and lattice vibrations. Spin ensembles dephase under stray nuclear baths, unless you refocus them with carefully timed pulses. And in cold atom lattices, the loss of a single atom acts as a local bath that drives the many-body field into dark, steady states with correlations you can image in situ. Each case reduces to the same triad. Identify the bath and its spectrum, measure the system's linear response, and check that the two are locked by fluctuation dissipation, where equilibrium holds and deviate, in diagnostic ways where it doesn't. For computation and control, openness is not the enemy but the resource you steer. Reservoir engineering builds baths with chosen spectra, so the only steady states are the targets you want: squeezed vacua, cat-like superpositions, topological dark states, and feedback turns measured noise into a knob that reshapes evolution in real time. Positivity-preserving master equations certify that your design won't predict negative probabilities. While non-equilibrium Green's functions on a closed-time path let you calculate currents, noise, and heating under strong drive without pretending the bath is sleepy, the experimental playbook is simple enough to memorize. Measure noise spectra and response functions side by side, and overlay the predicted fluctuation dissipation tie. Sweep temperature and drive to separate thermal from quantum parts of the noise. Deliberately inject calibrated noise at select frequencies to verify how damping and decoherence grow with the bath's spectral weight. Vary coupling bandwidth to move between Markovian and memoryful regimes, and watch information revivals or their absence. And when your model claims non-Gaussian noise, rare jumps or fat tails, check higher moments and full counting statistics instead of staring only at variances. Let the closing be quiet but firm. An open quantum field is not a broken ideal. It is the real thing. Fields live in worlds that listen and answer back. And the physics of baths and noise is the grammar that keeps those conversations legible. Once you learn to read kernels instead of wishing them away, dissipation and fluctuation stop being villains and become tools, knobs to stabilize, probes to diagnose, and when you are bold, levers to assemble steady states that no closed system could hold, so that your understanding slows to match reality's pace, even as your questions become sharper, and the soft hiss you once feared becomes the signal that tells you exactly how the field is learning from its surroundings. Where particle intuition misleads most. Begin with a confession that physics keeps trying to teach you. Many of the places your little bullet picture feels most natural are exactly where it fails most spectacularly, and learning to spot those traps turns confusion into craft. So let's walk through the landscapes where particle intuition misleads most and replace it with habits that actually predict what laboratories and telescopes see. First, the click in a detector is not proof that a tiny marble traveled a path. It is the end of a story where a field excited a large number of degrees of freedom in your apparatus until an irreversible mark was made. And between source and screen, the right object to follow is not a point, but a wave packet that spreads, interferes, and, crucially, can be decomposed differently by different observers. That last part hides a big trap. The very notion of how many particles are present depends on the motion and environment of the observer. Accelerate a perfectly empty detector through the vacuum, and it warms with a bath of excitations. A sober hint that particle number is not an absolute book, but a way of organizing field disturbances that works best for inertial observers in calm backgrounds. Even at rest, localization is slippery. You can aim a beam so finely that it paints sharp fringes. But for light, there is no position operator with all the comforting properties you learned from massive projectiles. And for neutrinos, the which particle am I seeing question has no single answer, because the flavor you label at the source is a superposition of different propagation modes. The pattern we measure is an interference of those modes, not a little sphere changing its identity mid-flight. Next, beware the urge to imagine hidden travelers inside your calculations. The internal lines in a diagram are not tiny couriers racing through the lab. They are integrals over possibilities, bookkeeping for how fields influence each other, and calling them virtual particles is only safe if you remember that they are never detected and need not respect on-the-nose energy-momentum relations. The same holds for vacuum fluctuations, which are not pairs popping in and out like gnats, but a compact way of encoding how the ground state's correlations modify forces and spectra when boundaries or fields are present. Tunneling is another place your bullet picture lies to you. Nothing bores through a wall. Instead, the wave function has support on both sides. The barrier reshapes phases and amplitudes, and detectors faithfully record the fraction that emerges. When you try to rescue the bullet by saying the particle borrowed energy for a short time, you're importing metaphor where phase evolution and boundary conditions are enough. In scattering, the temptation is to draw trajectories and ask where the tiny balls went. The right question is softer and more predictive. Which final patterns of fields have non-zero amplitude given the sources and symmetries? And how do those amplitudes interfere before you square them into probabilities? This is why two different routes to the same outcome can cancel or enhance, and why cross-sections are areas on a probability landscape, not literal target sizes. Quarks teach the harshest version of this lesson. They are excellent degrees of freedom inside a hadron or at small distances in a jet, but they do not exist as isolated bullets in the detector. Confinement turns the outgoing field lines into strings that snap into sprays of hadrons. So what you see are jets whose shapes and distributions encode the short-distance story, not the quarks themselves trying and failing to reach your calorimeter. In solids and fluids, your bullet picture will coax you to hunt for the fundamental particle that carries heat or sound, when the useful objects are quasi-particles, emergent excitations of many-body fields whose lifetimes and interactions depend on scale. They behave like particles only within certain windows, then decay into broader, wave-like disturbances. And good design means knowing where that crossover sits rather than demanding a point-like courier everywhere. Even forces can be misread when you lean on marbles. Pauli exclusion is not a mysterious repulsion between electrons. It is anti-symmetry in a spinor field that forbids sharing a quantum state. The resulting pressure supports white dwarfs because states are filled from the bottom up, not because electrons push each other like springs. Thinking this way lets you compute real numbers, equations of state and heat capacities, instead of inventing phantom forces. Causality is safer in field language too. Entanglement does not launch superluminal bullets carrying instructions. It arranges correlations that become visible only when classical information is compared, and every attempt to turn it into faster-than-light messaging smashes against the way local measurements leave marginal distributions unchanged. The particle picture makes you imagine flying messengers. The field picture keeps you honest about operations and correlations. Renormalization is another place bullets seduce and abandon you. Infinities in loop integrals aren't tiny particles misbehaving at short distances. They are a sign that your low-energy parameters must be defined by measurement and then used to predict scale dependence. The running of a coupling is not a swarm thickening or thinning. It is the way correlations at different distances reshape the effective strength of interactions when you probe with different resolutions. Infrared physics flips the trap the other way. A charged particle never travels alone. It drags an infinite cloud of soft radiation that changes what counts as a distinct final state. So if you insist on counting only events with exactly zero soft quanta, your theory will cough up divergences. The fix is to ask the right question. Sum over all outcomes indistinguishable to your detector, and the infinities evaporate because the mathematics finally matches the measurement. On the cosmological stage, time-dependent backgrounds manufacture or erase what you would happily call particles. A changing field value can turn vacuum fluctuations into classical perturbations, while curved geometry can make particle number non-conserved in any useful sense. If you stick with bullets, you'll lean on stories about creation and annihilation that invite paradox. If you stick with fields, you compute spectra and correlators that match the sky. Even simple wave mechanics resists the bullet instinct. A narrow packet that you launch to mark where the particle is immediately spreads, and the rate of spreading the wave phases accumulate and the response to slits or barriers are what set your downstream distributions. Clinging to a path and a point tempts you into asking which slit the particle really went through, a question the experiment refuses to answer, because the interference pattern is the evidence that the field took both openings in a superposed sense until your witch path probe forced a different evolution. The safer mindset is a three-step habit. Ask what the relevant field degrees of freedom are at the scale and environment of your experiment, and write the simplest effective description that respects the symmetries. Compute the inclusive observables that your apparatus actually resolves. Spectra, angles, correlations, summing over unobserved soft companions and averaging over phases you cannot track. Only at the end, when you interpret the results, use particle language where it is earned, long-lived, well-separated excitations, and abandon it where it lies. Short times, strong fields, changing backgrounds. Let the closing be soft but firm. Particle intuition is a good servant and a bad master. It helps when the world offers durable lumps you can label and count, and it hurts when you mistake a detector's click for a marble's path, a diagram's internal line for a traveler, or a global number for an invariant across frames. Tune your instincts toward fields, correlations, and the actual questions experiments ask, and the puzzles that once seemed like paradoxes. Vacuum that isn't empty, forces without pushes, creation without colliders, interference without paths. Settle into a calmer story where the world is continuous, your measurements are discrete, and the bridge between them is built from amplitudes, symmetries, and the discipline to follow what is measurable rather than what is comforting.